Everything in the universe is moving. Our planet spins, the Sun orbits the center of the Milky Way, and even our galaxy is racing through space at incredible speed. But this movement doesn't stop there. The very fabric of the universe is stretching, carrying galaxies farther and farther apart. If nothing is still, then the question naturally follows: where is it all going? For millennia, people believed the heavens were fixed, eternal and unchanging. Today, we know the opposite is true. Some galaxies are already slipping beyond our reach forever. Let's explore one of the deepest mysteries of science and discuss what we know about the ultimate fate of everything. The first clues, when astronomers noticed galaxies were not still. For a long time, people imagined the universe to be steady and unmoving. The stars, from our perspective on Earth, seemed to return to the same spots every night. The constellations looked fixed, like a great map drawn across the sky. This gave the sense that the heavens themselves were eternal, locked in place and unchanging. Even when telescopes began to reveal new wonders, most astronomers in the 19th and early 20th centuries assumed the same thing, that the universe was static, with stars and nebulae fixed where they were. The idea of motion on the grander scales, entire galaxies drifting through space, was simply not part of the picture.
The first cracks in this vision began with the study of light. Astronomers had learned that when you pass light through a prism, you can spread it into a spectrum of colors, revealing patterns of bright and dark lines. These lines were like fingerprints, showing the chemical makeup of stars and gases. But they also held another secret. When an object moved toward or away from us, the positions of those lines shifted slightly. This effect, known as the Doppler shift, meant that light carried within it a clue about motion. If stars or galaxies were moving, their light would tell us. In the early 20th century, a few astronomers began applying this method to the strange patches of light then called spiral nebulae. At the time, there was still debate about what these spirals were. Some believed they were nearby clouds of gas within our own Milky Way. Others argued that they were island universes, vast systems of stars far beyond our own galaxy. The technology to resolve the question was only just becoming available, and so the debate was fierce. But one thing could be tested even then: whether these spirals were moving. One of the first to notice something unusual was Vesto Melvin Slipher, an astronomer working at Lowell Observatory in Arizona. Starting around 1912, Slipher turned his telescope toward these spiral nebulae and measured their spectra. He expected small, random shifts, perhaps some moving toward us, some moving away as one might expect from objects drifting through the cosmos. Instead, what he found was startling. Almost all of the spirals he measured were shifted toward the red end of the spectrum. This meant they were receding, moving away from Earth, and not just slowly. Many were speeding away at hundreds of kilometers per second. This was far faster than stars within the Milky Way ever moved. Slipher's work was cautious, and for years it did not receive wide attention. He had no clear explanation for what he was seeing. But the data kept growing, and the pattern became hard to ignore. If these spirals were part of our own galaxy, their speeds made no sense. If they were separate galaxies, then the universe was far more dynamic than anyone had thought. The still universe was beginning to look restless. At the same time, technology and theory were beginning to move forward. In the 1920s, Edwin Hubble, working at Mount Wilson Observatory with the most powerful telescope of his day, the 100-inch Hooker telescope, made the breakthrough that settled the island universe debate. By studying certain stars called Cepheid variables within spiral nebulae, he measured their distances and proved they were far outside the Milky Way. These spirals were not clouds within our galaxy. They were galaxies themselves, each one containing billions of stars. The universe suddenly became much larger than previously imagined. And with that expansion of scale, Slipher's strange velocity measurements took on an entirely new meaning. Galaxies were not simply sitting in space, they were on the move. The cosmos was not a fixed stage, it was active, with galaxies streaming away into the distance. But this was a radical thought. The dominant view among physicists and astronomers was still shaped by centuries of tradition, and by the belief, even among giants like Albert Einstein, that the cosmos must be steady and eternal. Einstein himself, when he developed his equations of general relativity, had found that the mathematics suggested the universe should either expand or contract. Uncomfortable with this result, he introduced a special term, the cosmological constant, to force his model into balance. The idea of a universe in motion was so alien that even the greatest minds tried to hold it back, and yet the light from galaxies could not be silenced. As more data was gathered, the trend became impossible to deny. Most galaxies were redshifted, and the farther away they were, the greater the redshift appeared to be. This suggested that not only were galaxies moving, their motion followed a pattern. The universe itself might be stretching, carrying galaxies apart like raisins in rising bread dough. But in the early stages, this interpretation was not yet clear. For many astronomers, the first clues were unsettling rather than illuminating. The static universe was unraveling, and it was not obvious what would replace it. Slipher's measurements relied on patient nights at the telescope, carefully photographing faint spectra, sometimes over the course of dozens of hours. His dataset was not vast, just a few dozen galaxies at first, but it was enough to challenge centuries of assumptions. The motion of galaxies was not something obvious to the naked eye. It revealed itself only in the delicate fingerprints of light, requiring careful analysis and trust in a new kind of evidence. Many resisted, skeptical that so much could be concluded from shifts of color too small for the eye to see. When Slipher and Hubble, in different ways, showed that galaxies were not still, they were not just changing astronomy. They were changing humanity's place in the universe. From that moment on, the stars above were part of a grander story, one that was unfolding on scales far beyond imagination. Hubble's leap, redshifts as a measure of distance and motion. For centuries, astronomers had struggled with the problem of measuring distances in space. While methods for nearby stars existed, there had been no reliable way to measure objects beyond the boundaries of the Milky Way. Hubble solved this problem by using Cepheid variables. These stars pulsate in brightness in a way that is directly linked to their true luminosity. By measuring how fast a Cepheid pulsated, astronomers could determine how bright it actually was, and by comparing this with how bright it appeared from Earth, they could calculate its distance. It was like finding a cosmic ruler hidden in the sky. Hubble applied this method to galaxies that had once been thought to be nebulous clouds. His measurements showed that these objects were millions of light years away. This alone was a staggering discovery, for it expanded the known universe by unimaginable scales. But it was only the first step. With distances in hand, Hubble could now compare them to the velocities that Slipher and others had measured through redshifts. The data suggested that galaxies were not just drifting in space, but that their motion followed a law. If you plotted their distances against their speeds, the points formed a straight line. Nearby galaxies moved away slowly, while far-off galaxies sped away more quickly. The relationship was simple, almost elegant, but its meaning was revolutionary. The reaction to Hubble's findings was mixed at first. Some welcomed the clarity it brought to the puzzling redshifts. Others resisted, unable to let go of the idea of a static cosmos. If the universe was stretching now, did that mean it had once been smaller? Did it have a beginning? If so, what had set it into motion? These were not questions most astronomers had expected to face. Yet Hubble's evidence was plain, and as more data accumulated, it became impossible to deny. The redshifts were real. The relationship between distance and velocity held true. Hubble himself was cautious in his interpretations. He presented the data, showed the pattern, and allowed others to wrestle with the deeper meaning. He did not claim to have solved the riddle of the cosmos, but his work forced the scientific community to take seriously a picture that only a few years earlier would have seemed unthinkable. After seeing Hubble's evidence, Einstein is said to have called his introduction of the cosmological constant, the fudge factor to keep the universe balanced, the greatest blunder of his life. For theologians, it raised the possibility of a creation moment, a beginning in time. For physicists, it demanded new theories about the origin and fate of the cosmos. For ordinary people, it altered the sense of place in the universe. It is easy today to take the idea of an expanding universe for granted. High schoolers learn about it as a basic fact, and animations of galaxies moving apart are common in documentaries. But in Hubble's time, this was a radical departure from everything that had been believed. Cosmic expansion versus motion through space. The human mind is used to thinking in terms of objects moving in a fixed arena. The Earth spins, planets revolve around the Sun, and comets fly through the solar system. All of these are motions through space. But expansion is the arena itself stretching. The dancers are simply going along for the ride. There is no central point from which the galaxies are rushing outward. Every point sees the others receding. There is no center of the universe where the expansion began. The expansion is everywhere. This helps explain why the Earth does not sit in some privileged spot. To early astronomers, the fact that galaxies all seem to be receding from us could have suggested that we were at the center of the universe. But wherever you stand in an expanding universe, you will see the same pattern, galaxies receding, with the farthest ones moving the fastest. It is not that we are special, it is that space behaves the same way everywhere. An important detail lies in the difference between local motion and cosmic expansion. Within galaxies, stars orbit around their centers. Within clusters of galaxies, the galaxies themselves can orbit each other or collide. These are examples of motion through space. Gravity binds systems together, resisting the pull of expansion. That is why the Milky Way is not tearing itself apart, and why our galaxy and the neighboring Andromeda galaxy are actually moving toward one another, not away. On small scales, gravity is stronger than expansion. It holds objects together. Expansion only dominates on the largest scales, across the great stretches between galaxy clusters, where gravity is too weak to keep things bound. There, the stretching of space takes over. To imagine this more clearly, think again of raisins inside a rising loaf of bread. As the dough rises, the raisins move farther apart, but within each raisin, nothing changes. The material inside the raisin is held together by its own forces, so it does not expand along with the dough. Galaxies are like those raisins. Their stars, gas and dust are held together by gravity. The galaxy does not expand internally. Instead, galaxies are carried apart as the dough of space grows. This distinction is vital because it shows how expansion is not simply motion, but a change in the structure of the universe. That is why no galaxy needs to burn fuel or expend energy to move away. For observers, this creates some strange consequences. If you look far enough away, the expansion can make galaxies recede faster than the speed of light. At first, this sounds impossible, since nothing is supposed to move faster than light. But here again, expansion is not motion through space. The galaxies themselves are not breaking the speed limit. Instead, it is the space between us and them that is growing so quickly that light cannot bridge it. This is why there are parts of the universe we will never see, no matter how powerful our telescopes become. Beyond a certain distance, expansion outpaces light itself, placing those regions forever out of reach. The recognition of expansion also changes how we think about the past and future. If space is stretching now, it must have been smaller in the past. If we rewind the clock, the galaxies get closer and closer until they converge in a single point of origin. This is the seed of what would become the Big Bang idea, the notion that the universe began in a hot, dense state and has been expanding ever since. But this realization only makes sense once you understand that expansion is not about galaxies moving outward into empty space. It is about the creation of new space. There is no edge to the universe that is expanding into something beyond. Just as the surface of a balloon expands without having an edge in 2 dimensions, the universe expands without requiring an outside to grow into. This is perhaps the hardest thing for the human imagination to accept, because in our everyday world, everything grows into something else. A soap bubble expands into the air. A loaf rises in the oven. A city spreads into the countryside, but the universe does not expand into anything. The cosmic microwave background, the echo of a moving universe. Long before telescopes revealed distant galaxies, the universe itself carried within it a memory of its beginnings. That memory is written in light, stretched thin by billions of years of expansion, now bathing all of space in a faint glow. This glow is the cosmic microwave background, or CMB, and it stands as one of the most powerful pieces of evidence that the universe has been expanding since its earliest moments. It is not the light of stars or galaxies, but the afterglow of the universe, a fossil of the time when everything was hot, dense, and closely packed. To understand why the CMB matters, it helps to imagine the universe in its youth. After the first instant of expansion, the cosmos was unimaginably hot and filled with a dense soup of particles and light. Photons could not travel freely. They scattered constantly off the charged particles around them, light trying to shine through a thick fog. The universe was opaque, glowing with its own heat, but nothing could move through it without being stopped and redirected. For hundreds of thousands of years, this was the state of things, a churning, glowing plasma where matter and light were bound together. As the universe stretched, however, it cooled. Expansion thinned out the dense plasma, and eventually, about 380,000 years after the beginning, the temperature dropped low enough for electrons and protons to combine into neutral atoms. This moment is known as recombination. When it happened, light was finally free to move unhindered. Photons no longer bounced endlessly from particle to particle. Instead, they streamed outward, filling the universe with a sea of radiation. That light has been traveling ever since, stretched into microwaves by the continuing expansion of space. When we tune our instruments today, we can still catch it, the faint afterglow of the early universe, reaching us from every direction. The discovery of this background radiation in 1965 was an accident. Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, were trying to eliminate a mysterious noise from their measurements. No matter what they did, the signal persisted, coming evenly from every patch of the sky. At first, they suspected some mundane cause. They even cleaned out pigeon droppings from the antenna, thinking it might be interfering. But the noise remained. It was not local. It was cosmic. Unknowingly, they had stumbled upon the glow of the universe's beginning. Other teams of scientists had predicted such radiation should exist if the universe had once been hot and dense. Now, the prediction had become reality. The CMB confirmed what Hubble's redshifts had first suggested. The universe had been expanding from a hotter, denser state. It provided a kind of map, a snapshot of the universe when it was only a few 100,000 years old. For the first time, astronomers could see not just that the universe was in motion, but how that motion had shaped its earliest structures. When sensitive satellites like COBE, WMAP, and later Planck mapped the CMB in detail, they revealed something striking. The radiation was almost perfectly uniform, the same temperature in every direction, but not completely so. There were tiny variations, slight hot and cold spots at the level of 1 part in 100,000. These minute differences were the seeds of all later structure. Where the glow was slightly denser, matter would later gather into galaxies and clusters. Where it was slightly thinner, cosmic voids would eventually form. In these faint patterns lay the fingerprints of a universe in motion, already beginning to shape the grand architecture we see today. The CMB also gave astronomers something they had never had before, a frame of reference. Normally, in the vastness of space, there is no absolute sense of motion. One could always argue that movement is relative. You are moving compared to me, I am moving compared to you. But the CMB provides a universal backdrop, a kind of rest frame for the cosmos itself. By measuring how the glow appears in different directions, scientists can tell that our galaxy, and indeed our entire local group of galaxies, is moving relative to this ancient light. In one direction, the radiation is slightly hotter, shifted toward the blue, while in the opposite direction it is slightly cooler, shifted toward the red. This dipole pattern tells us that we are not stationary, but streaming through space at hundreds of kilometers per second, carried along in the larger flows of the universe. The CMB is just faint microwave radiation, invisible to human eyes, yet within its patterns lies the story of cosmic expansion. Its smoothness across the sky tells us that the cosmos, even in its infancy, was remarkably uniform. Its tiny fluctuations tell us that structure was already beginning to form, laying the foundation for galaxies, stars, and eventually life. And its slight asymmetries in temperature across the sky allow us to measure our own motion against the grand sweep of cosmic history. In many ways, the CMB is like a photograph of the universe as a baby. It is frozen light, carrying the imprint of an age long before the first stars were born. Every time astronomers study it more closely, they peel back another layer of the universe's story. It confirms not only that expansion has been taking place, but that the laws of physics have held steady since those earliest moments. Without it, we might still be debating whether the cosmos had a beginning at all. With it, we can trace our origins back to a fiery dawn. And yet, what is perhaps most humbling is how ordinary the glow seems. It fills every corner of space equally. If you had the right kind of eyes, you would see the night sky glowing faintly everywhere, not dotted with stars, but bathed in a smooth background light. It does not single out our galaxy or our place in the universe. It is not brighter here, dimmer there. It simply exists, a universal reminder of where everything began. Every galaxy, every cluster, every void has grown from the tiny seeds frozen in that ancient glow. Every motion we see today, the rushing apart of galaxies, the streaming of clusters, is a continuation of the movement first captured in that snapshot of the young cosmos. The surprising discovery: expansion is accelerating. By the end of the 20th century, astronomers had grown used to the idea that the universe was expanding. Hubble's law had become a cornerstone of modern cosmology, and the CMB had confirmed that this expansion stretched all the way back to the earliest times. But while the fact of expansion was accepted, a deeper question remained. How was it changing? Gravity, after all, is a universal force. Every galaxy, every cluster of galaxies, pulls on every other. Over billions of years, those pulls should gradually slow the expansion. Astronomers expected that if you measured carefully enough, you would see the universe's growth rate decelerating, tugged back by the combined weight of all its matter. The only debate was how much it was slowing and whether it might eventually reverse. The late 1990s brought a shocking answer. When teams of astronomers set out to measure the rate of slowing, they discovered instead that the expansion of the universe was not decelerating at all. It was accelerating, speeding up as time went on. Rather than galaxies pulling one another back, they were flying apart faster and faster. The cosmos was rushing apart as though some invisible hand were pushing it outward. Certain kinds of supernovae, known as type Ia supernovae, are among the most useful tools for measuring cosmic distances. They occur when a white dwarf star in a binary system gathers enough matter from its companion to ignite a runaway explosion. Because this process happens at a very specific mass, the explosions reach nearly the same brightness every time. This makes them standard candles, objects whose true brightness is known. By comparing their intrinsic brightness with how bright they appear from Earth, astronomers can determine their distances with high precision. Two major research groups in the 1990s, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, set out to use these stellar explosions to track the history of cosmic expansion. Their plan was to observe distant type Ia supernovae, measure their distances and compare them to their redshifts. With enough data, they could see whether the expansion was slowing as expected. Years of effort went into building these samples, gathering light from explosions billions of light years away. The supernovae were faint and the observations were painstaking. When the results came in, they were bewildering. The supernovae appeared dimmer than they should have been if the universe's expansion were merely slowing down. The only explanation was that those galaxies were farther away than expected, meaning the expansion must have sped up over time. The light had traveled through a universe that had stretched more than anticipated, leaving the explosions looking fainter. What the astronomers found was the opposite of what they had set out to confirm. Instead of a universe held back by gravity, they had uncovered a universe driven by something unseen, accelerating its growth. This realization struck at the heart of cosmology. For decades, scientists had imagined the universe as a battle between expansion and gravity. The Big Bang had set things in motion, and gravity was thought to be slowing it down. If the universe had enough mass, gravity might eventually halt expansion and cause everything to collapse back in a big crunch. If not, expansion would continue forever, though at an ever-decreasing rate. Acceleration had not been part of the conversation. It seemed almost absurd. How could the universe, with no obvious fuel or engine, speed itself up? Where was it getting the energy? But the data was clear. The discovery was announced in 1998, and it immediately became one of the greatest puzzles in modern science. To account for the accelerating expansion, astronomers revived an old concept: Einstein's cosmological constant. After Hubble's discovery, Einstein had discarded it, calling it a mistake. But now, something like it seemed necessary again. If the universe was accelerating, then some kind of repulsive force must be at work, countering gravity and driving galaxies apart. This mysterious energy became known simply as dark energy. Dark energy could not be seen directly. It did not clump together like matter. Instead, it seemed to be a property of space, an energy woven into the very fabric of the cosmos. As space expanded, dark energy did not thin out the way matter or radiation did. Instead, it stayed constant, or perhaps even grew, making its influence stronger and stronger as the universe aged. This would explain why acceleration appeared only in the later history of the cosmos. Early on, matter and radiation dominated, but as expansion diluted them, dark energy took over, pushing the universe apart ever faster. If dark energy continued its work, galaxies would drift farther and farther apart until only our local group remained visible. The night sky would eventually empty, leaving future observers stranded in an apparently dark, lonely cosmos, unaware of the larger universe that once surrounded them. In even more extreme scenarios, if dark energy grew stronger over time, it could tear apart galaxies, stars, planets, and even atoms themselves in a distant event some called the Big Rip. But for all the speculation about its consequences, the true nature of dark energy remained hidden. Was it really Einstein's cosmological constant, a fixed energy of space? Was it some new kind of field or force? Could it be a sign that our understanding of gravity was incomplete, that Einstein's equations broke down on cosmic scales? The acceleration of the universe did not just add a new detail to cosmology, it opened a chasm of uncertainty at the very foundations of physics. For the teams who discovered it, the moment was both thrilling and unsettling. They had set out to measure a gentle slowing and instead found a runaway speeding. The result was so unexpected that the astronomers checked their data repeatedly, searching for errors. But the evidence grew stronger with every new observation. Other groups confirmed the findings. Satellite missions measuring the CMB supported the picture. Large surveys of galaxy clustering lined up with the same conclusion. The universe was accelerating and no one could deny it. In 2011, the Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees for their discovery. It was an acknowledgement of one of the most surprising turns in the history of science. Yet even as the prize was awarded, the mystery deepened. Dark energy accounted for roughly 70% of the universe's total content, dwarfing ordinary matter and even dark matter. Most of what made up the cosmos was invisible, untouchable, and poorly understood. Humanity had revealed a vast new piece of reality, but it was a piece wrapped in shadow. What lies beyond the observable universe? The light from distant galaxies has traveled for billions of years before finally reaching us, carrying with it a story of how the universe once was. But no matter how powerful our telescopes become, there is a boundary we cannot cross, the edge of the observable universe. It is a limit set by the speed of light and the age of the cosmos. Beyond this horizon, space continues, but its contents remain hidden. Astronomers often begin with a simple assumption, that the parts of the universe we cannot see look more or less like the parts we can. This idea, called the cosmological principle, is built on the belief that the universe is uniform and has no special center or edge. When we point our instruments in different directions, the overall picture seems to support this. On very large scales, galaxies are spread out in a way that appears even. This suggests that the hidden parts of the cosmos may follow the same rules as the visible parts. Yet, as with many things in science, what seems simple may hide deeper surprises. One of the biggest reasons to question what lies beyond is inflation. Inflation helps explain why the universe looks so uniform, but the part of the cosmos we can observe might be only a tiny fraction of a much larger whole. In fact, if inflation occurred, then the universe is likely vast beyond imagination, possibly infinite. Our observable bubble would then be like a single patch on an endless quilt. If the universe does extend far beyond what we see, could those unseen regions be different from our own? Some scientists suggest that inflation might not have stopped everywhere at once. Instead, it could continue in far-off regions, creating vast domains with different properties. The constants of physics that feel fixed to us, such as the strength of gravity or the charge of an electron, could, in principle, vary elsewhere. To us, the night sky appears consistent and predictable, but beyond our horizon, the rules of reality might not be the same. The observable universe, with its hundreds of billions of galaxies, might seem unimaginably large, but it could be just a drop in an ocean of space. If there are regions beyond our view, they are forever cut off from us by distance and time. The boundary of the observable universe is not a physical edge, but a horizon of knowledge. It defines what we can know. Some researchers take this line of thought further, imagining that beyond our visible patch there might be multiple universes, each with its own version of reality. This is called the multiverse. In this picture, our universe is just one bubble among countless others, each with its own physics, its own history, perhaps even its own forms of life. It is a bold and controversial idea, one that stretches far beyond what observations can currently prove. But it is also a natural extension of inflation, which seems to suggest that the creation of space could be happening endlessly, spawning new universes far beyond our reach. We live on a small planet orbiting an ordinary star in one galaxy among billions, inside a universe that may itself be only one part of a grander structure we can never fully see. Our perspective is limited. Our instruments, no matter how advanced, can only look so far. The question of what lies beyond may never be answered with certainty. It is, in many ways, the ultimate horizon. Still, by studying the clues we can reach, by pushing our observations to greater distances and refining our theories, we continue to stretch that boundary as far as it will go, and with each step, the unseen beyond becomes a little more real. The case for dark energy, multiple independent clues. When the idea of dark energy first surfaced, it was not embraced easily. The discovery that distant supernovae were fainter than expected was so shocking that many wondered if it was an error. Could the stars have been obscured by dust? Could there have been a miscalculation in how their brightness was measured? To trust such a radical idea, scientists needed multiple lines of evidence, independent of one another, all converging on the same strange conclusion. Over the years, that evidence began to pile up. One of the most important confirmations came from the CMB. If the universe contained only matter and no dark energy, the size and shape of the ripples would look very different. Yet when scientists compared the observed map of the CMB with theoretical models, the fit only worked if there was a mysterious energy component driving accelerated expansion. This was a completely independent way of probing the cosmos, far removed from exploding stars, yet it pointed to the same answer. Another piece of evidence came from galaxy clustering. Galaxies are not sprinkled randomly across space. They gather in filaments, clusters, and vast web-like structures that stretch across hundreds of millions of light years. The way these structures form depends on how fast the universe is expanding. If expansion was slower, gravity would have more time to pull matter together, creating denser clusters. If expansion were faster, matter would be stretched apart before gravity could fully do its work. By mapping the large-scale distribution of galaxies, astronomers could infer how the expansion changed over time. These surveys consistently showed that galaxies were arranged in ways that only made sense if something was speeding the universe up. Within this clustering pattern, researchers also found a special kind of marker called baryon acoustic oscillations, or BOs. These are like frozen sound waves imprinted into the fabric of the universe. In the very early cosmos, before atoms formed, matter and light were tightly bound together in a hot, dense plasma. Waves of pressure rippled through this plasma much like sound through air. When the universe cooled and atoms formed, these ripples left behind a preferred spacing in the distribution of galaxies, a faint but detectable standard ruler written across cosmic space. By measuring this pattern, astronomers could compare how the scale of the universe had grown at different times. The BOs provided a completely new, independent check, and once again, the results lined up with the idea of accelerated expansion. Together, these clues created a picture that was impossible to ignore. Each method had its own assumptions and uncertainties, but the fact that they all converged on the same conclusion gave scientists confidence that this was not a mistake. Something real and profound was shaping the cosmos. Dark energy is not directly detected, it reveals itself only through the stretching of space. We cannot put it in a bottle and we cannot recreate it in a laboratory. Yet its fingerprints are written across the cosmos. The case for dark energy became one of the strongest in modern science because of this remarkable convergence. Each piece of evidence acted like a witness, independent of the others, yet all telling the same story: vacuum energy, Einstein's cosmological constant revisited. When Einstein developed his general theory of relativity, it described gravity not as a force pulling on objects, but as the bending and warping of space and time themselves. It allowed astronomers and physicists to rethink the way the cosmos functioned. Yet when Einstein applied his equations to the whole universe, he ran into a puzzling result. His math suggested that the universe could not remain perfectly static. To avoid this, Einstein added the cosmological constant. Today, this idea is often discussed in terms of vacuum energy. In quantum physics, the vacuum is not truly empty. Even in regions where no matter or radiation exists, quantum fields still fluctuate. Particles and antiparticles can briefly appear and vanish, as though space is never completely still. These fluctuations, according to theory, contribute to an underlying energy density of space itself. When added up across the universe, this vacuum energy could act like a kind of pressure, one that accelerates expansion. The cosmological constant is the simplest way to describe this effect. It represents a fixed energy density that is built into the fabric of spacetime. Unlike matter or radiation, which dilute as the universe expands, the cosmological constant stays constant. Its strength per unit volume does not decrease. As space grows, more of this vacuum energy appears, and so the repulsive push becomes increasingly dominant over time. This matches the observed acceleration, which is why many scientists see the cosmological constant as the most straightforward explanation for dark energy. But there is a problem. When physicists try to calculate the vacuum energy predicted by quantum theory, the result is staggeringly large, many orders of magnitude greater than what we actually observe in the cosmos. The predicted number is so huge that it would have torn the universe apart instantly, preventing stars and galaxies from ever forming. Instead, the observed value of dark energy is extremely small, yet non-zero. Reconciling this enormous mismatch is a puzzle, sometimes described as the worst theoretical prediction in science. This tension raises difficult questions. Is vacuum energy truly the source of cosmic acceleration, or is something else at play? Could our understanding of quantum fields be incomplete, or might the cosmological constant be real, but fine-tuned in some mysterious way that we do not yet understand? For now, the cosmological constant remains the leading model, not because it is fully satisfying, but because it fits the data with the least assumptions. The history of the cosmological constant also illustrates the strange ways science can unfold. What began as a mathematical patch to uphold a false belief in a static universe became, nearly a century later, a central piece in explaining why the universe expands faster and faster. Einstein might not have anticipated this outcome, but his equations were flexible enough to accommodate it. This speaks to the power of mathematics in capturing truths about nature, even when scientists misinterpret their own tools. Empty space itself, something that seems like nothing at all, may be the most powerful driver of cosmic evolution. What we call nothing can be filled with structure and effect, shaping the fate of everything. Far from being Einstein's greatest mistake, it may turn out to be one of his greatest legacies, a clue left behind for future generations to decode, pointing to the hidden energy of the vacuum and its role in the grand story of the universe. Quintessence. Could dark energy change with time? What if the force behind acceleration isn't frozen in time, but instead evolves as the universe changes? This is where the idea of quintessence enters the picture, a term borrowed from ancient philosophy, where it once meant a fifth element beyond earth, air, fire, and water. In modern physics, it has come to mean a dynamic, changing form of dark energy. The basic idea of quintessence is that dark energy could come from a field, much like the fields that underlie particle physics. For example, just as the Higgs field permeates space and gives particles mass, quintessence would be a cosmic field stretching across the universe, slowly rolling and shifting over billions of years. Unlike Einstein's cosmological constant, which is simply built in as an unchanging property of empty space, this kind of field could rise or fall in strength depending on the conditions of the cosmos. That means the repulsive push driving galaxies apart might not always be the same. It could have been weaker in the past and stronger now, or the other way around. If dark energy is truly constant, then the universe's destiny is fairly clear. Expansion will go on forever, growing faster and faster, until galaxies drift so far apart that no new stars are born and the night sky becomes empty. But if quintessence is real, the story becomes less certain. Imagine if dark energy gradually weakens over time. In that case, gravity could begin to reassert itself, slowing the expansion and perhaps even reversing it someday. The cosmos could eventually collapse back in on itself. On the other hand, if quintessence grows stronger over time, it could drive the expansion into a runaway effect, eventually leading to the Big Rip. Some cosmologists point to observations that are consistent with a constant dark energy, while others argue that current data leaves enough wiggle room for quintessence to still be possible. The truth is, the universe has only been accelerating for the last few billion years, and our window into this phenomenon is relatively narrow compared to the cosmic timescale. It's like trying to judge whether a car is speeding up or slowing down by glancing at it for a split second. The data we gather from supernovae, the CMB and galaxy clustering are all snapshots in cosmic time. To know for certain if dark energy is changing, we need more precise observations, stretching across even greater distances and epochs. The scientific challenge of studying quintessence lies in how subtle the differences are between it and a cosmological constant. Both can produce an accelerating universe, but the details diverge when you look closely at how galaxies cluster together, how large-scale structures grow, and how the CMB is shaped by the passage of billions of years. In principle, if quintessence were real, we might detect small variations in the equation of state that describes dark energy, the relationship between its pressure and density. A cosmological constant always has the same value for this relationship, while quintessence would allow it to drift. That drift is exactly what researchers are hunting for. To explore this possibility, astronomers have designed ambitious surveys and telescopes aimed at mapping the universe in more detail than ever before. Projects like the Dark Energy Survey, Euclid, and the Vera Rubin Observatory are not just cataloguing galaxies for the sake of counting them. They are trying to measure the subtle fingerprints of cosmic acceleration and see whether dark energy has truly been constant or has shown signs of changing over billions of years. Some of these studies also look at BAOs. By comparing them at different points in time, scientists hope to see whether the push of dark energy has varied. Interestingly, quintessence is not the only time-varying idea proposed to explain dark energy. There are even more radical versions, such as phantom energy, where the pressure is so negative that it leads to catastrophic scenarios. There are also tracker fields, where the dark energy field naturally evolves in a way that mimics matter and radiation at early times before dominating later. Each of these models has its own predictions for how the universe evolves, and each one paints a different picture of what lies billions or trillions of years ahead. Some scientists are cautious about embracing quintessence. They point out that the simplest explanation fits current data well and avoids unnecessary complications. Others, however, argue that simplicity is not always the same as truth. After all, many discoveries in science began with recognizing that reality was more complex than first believed. If dark energy really is dynamic, then the implications reach far beyond cosmology. It could mean that our universe is shaped by fields that may even link to theories of particle physics, string theory, or ideas about multiple universes. Phantom energy and the Big Rip hypothesis. The Big Rip scenario begins with the idea of phantom energy, a form of dark energy even more powerful than the already puzzling cosmological constant. Phantom energy suggests that not only is space expanding, but the very rate of expansion could increase without bound, leading to a future where everything, galaxies, stars, planets, molecules, and even the building blocks of matter, gets torn apart. If dark energy changes with time, its behavior can be described with what scientists call the equation of state. This is a number that tells us how much pressure dark energy exerts compared to its energy density. For a cosmological constant, this number is exactly 1. If the number is greater than 1, we get quintessence. But if the number is less than 1, we enter the realm of phantom energy. If dark energy's repulsive force grows faster than gravity can hold matter together, it eventually overwhelms everything. Step by step, it escalates from cosmic scales down to the very fabric of matter. Cosmologists studying this possibility have worked out a timeline for how such a big rip could unfold, assuming phantom energy exists. Billions of years from now, galaxies that are currently bound into clusters would be ripped away from each other. Later, individual galaxies themselves would be torn apart, as the phantom energy outpaces the gravity-binding stars to their galactic homes. After that, stars would lose their planets as solar systems dissolve under the strain of expanding space. Then stars themselves, once stable through their own internal gravity, would be pulled apart. Eventually, the destruction would reach molecules, atoms, and finally the subatomic particles inside protons and neutrons. In the final moments before the ultimate end, the very laws of matter would fail as space itself unravels. Unlike a sudden event such as a supernova or a black hole collision, the Big Rip is a slow tightening of the universe's expansion, a long build-up toward final disassembly. To observers in the far future, the signs would be unmistakable. First, distant galaxies would disappear beyond the cosmic horizon faster than ever before. Then, closer galaxies would begin to stretch apart. Even the familiar constellations in the night sky would warp and dissolve as stars drifted away at impossible speeds. Finally, in the last stretch of time, perhaps only minutes or seconds before the end, everything smaller and smaller would succumb, until no structure at all remained. Of course, the Big Rip is only one possible outcome, and it depends entirely on whether phantom energy truly exists. Current observations allow scientists to measure the dark energy equation of state with increasing precision, and so far it seems very close to 1. Whether it is slightly greater than 1, favoring quintessence, exactly 1, favoring the cosmological constant, or slightly less than 1, favoring phantom energy, is still uncertain. The difference may sound small, but over cosmic timescales, it changes the fate of everything. If the number is even just a little below 1, then phantom energy will eventually dominate, and the Big Rip becomes unavoidable. Everything we know, stars, atoms, even the forces that bind them, could be temporary in a universe ruled by phantom energy. The Big Rip is not a prophecy, but a hypothesis built from extrapolation. It depends on assumptions that may or may not hold true, and it may never come to pass. But its very possibility reshapes how we think about cosmic destiny. Modified gravity. What if Einstein's equations need updating? Modified gravity shifts the focus away from dark energy and toward the possibility that our theory of gravity is incomplete. Just as Newton's law of gravity was replaced by Einstein's relativity when we probed deeper into the universe, perhaps relativity itself is only an approximation of something even more fundamental. The thought may seem radical, but history suggests it is not impossible. Physics has been rewritten before. The problem comes down to scale. Einstein's relativity has been tested in environments where the gravitational pull is strong, around planets, stars, and even black holes. But the accelerating universe reveals itself in the weakest possible regime, on scales spanning billions of light years. No laboratory can replicate such conditions. It is entirely possible that gravity behaves differently when stretched across the cosmos than it does in our local neighborhood. If so, the strange push we call dark energy may not be an extra ingredient of the universe at all. It could be a sign that our gravitational recipe is slightly off. One of the earliest ideas along these lines is known as RFR, gravity. In Einstein's equations, the geometry of spacetime is described using a mathematical object called the Ricci scalar, symbolized by R. In relativity, the equations depend linearly on R, a simple relationship. Modified theories suggest that maybe the dependence is more complicated, perhaps involving higher powers of R or other functions entirely. Such changes sound small on paper, but their consequences can be dramatic on cosmic scales. In some versions, the universe naturally begins to accelerate at late times without needing any dark energy. Another well-known modification is called MOND, short for Modified Newtonian Dynamics. Originally proposed in the 1980s, MOND was designed to explain the strange motions of stars in galaxies without invoking dark matter. According to Newton and Einstein, stars at the edges of galaxies should move more slowly than those near the center. But observations show they move much faster than expected. The mainstream explanation is that galaxies sit inside giant halos of invisible dark matter, which provide extra gravity. MOND suggests instead that gravity changes behavior when accelerations become extremely small. While MOND is not usually used to explain cosmic acceleration, it laid the groundwork for questioning whether dark phenomena, dark matter, and dark energy might be signs of our incomplete gravity theories. Building on these ideas, some physicists propose entire new frameworks for gravity. One of the most famous is scalar tensor theories. In these models, gravity is not carried only by the curvature of spacetime, as Einstein described, but also by an additional field that pervades the universe. This field can act repulsive on large scales, driving the acceleration of expansion. In essence, instead of postulating dark energy as an independent ingredient, the acceleration arises naturally from the way gravity itself operates. Observationally, these alternatives must walk a tightrope. They need to reproduce all the successes of Einstein's relativity where it has been tested, while also producing differences only visible on cosmic scales. For example, when we watch the dance of binary pulsars, Einstein's theory predicts their orbital decay due to gravitational waves with incredible precision, and observations match perfectly. Any modified theory that disagrees here is immediately ruled out. The challenge is to craft models that look indistinguishable from relativity in the local universe, but diverge gently across billions of light years. Large-scale surveys of galaxies are key to testing these ideas. If gravity is different across cosmic distances, the way structures grow should also differ. Some modified gravity models predict faster growth, others slower. Future missions are designed to measure such growth patterns with exquisite detail. By comparing these observations with predictions, scientists hope to catch subtle fingerprints that might betray a deviation from Einstein's rulebook. Gravitational waves also offer a new testing ground. In relativity, gravitational waves travel at the speed of light and carry energy in specific ways. Modified gravity theories often predict small changes in their speed or how they decay as they move across the universe. When astronomers observed gravitational waves from merging neutron stars in 2017, along with a burst of light arriving at nearly the same time, they confirmed that gravitational waves move at the same speed as light to an extraordinary degree of accuracy. This result instantly ruled out many modified gravity theories, but some possibilities remain. One intriguing concept is massive gravity. In Einstein's relativity, the graviton, the hypothetical particle that mediates gravity, is massless, allowing its force to extend indefinitely. But what if the graviton had a tiny mass? Gravity would then weaken over cosmic distances, altering the universe's expansion. Such theories predict a universe that could mimic the effects of dark energy without actually requiring it. The mathematics of massive gravity is notoriously complex, but it is being explored with increasing interest. Skeptics of modified gravity point out that dark energy, despite its mystery, is the simpler explanation. By adding one new ingredient, vacuum energy or something like it, we can keep Einstein's successful equations intact. Modified gravity, in contrast, often demands entirely new mathematical frameworks, additional fields, or elaborate constructions that can seem contrived. The principle of scientific simplicity, of Occam's razor, often leans toward the dark energy view. Yet the cosmological constant, the most basic version of dark energy, comes with its own profound puzzles. Quantum physics predicts that empty space should have an enormous amount of energy. To match reality, almost all of this energy would have to cancel out, leaving a tiny leftover. This seems unnaturally fine-tuned, like balancing a pencil on its tip. Modified gravity offers a way to bypass this problem by changing the rules altogether. When should scientists invent new unseen entities, and when should they rewrite the laws themselves? In the past, both approaches have had successes. When Uranus's orbit looked odd, astronomers proposed a new planet, Neptune, and they were right. But when Mercury's orbit didn't match Newton's predictions, the solution wasn't a hidden planet, but a new theory of gravity. Dark energy could be our Neptune, or it could be our Mercury. The only way to know is to keep observing, testing, and pushing theories to their limits. Einstein's equations have survived every challenge so far, yet nature might still have surprises in store. The accelerating universe is one such surprise, and whether it points to an unseen energy or a new understanding of gravity itself remains one of the biggest open questions of modern science. The cosmic horizon, the limit of what we can see moving away. If the universe were static, if space did not change or expand, then the size of the observable universe bubble would simply be the speed of light multiplied by the age of the universe. In other words, it would be about 13.8 billion light-years across in radius. But because the universe is expanding, the true size is much larger. The light from those distant galaxies has been stretched along the way, and the space between us and them has grown while the light was in transit. This means that the farthest objects we see today are not 13.8 billion light-years away, but closer to 46 billion light-years. It sounds contradictory, but it reflects the strange geometry of an expanding cosmos. There is the particle horizon, which is the limit of how far light has traveled since the Big Bang, and there is the event horizon, which marks the farthest point from which we will ever receive information. These horizons are not the same. though both define boundaries to our observable universe. Together, they frame the limits of human knowledge. The universe may be infinite, stretching on without end, but for us, it is always bound by horizons we cannot cross. Galaxies inside the event horizon today will continue sending us signals into the future. Galaxies outside it are already lost to us, even if their ancient light is still on its way. We assume the universe continues beyond our horizon in roughly the same way it looks inside, but this principle is still an assumption, and beyond the cosmic horizon, it cannot be tested. Some scientists wonder whether the laws of physics themselves might vary in those unseen regions. Could the strength of gravity or the value of the speed of light be slightly different elsewhere? Could there be areas where dark energy behaves in new ways, or where structures never formed into galaxies at all? As space continues to expand, more galaxies will eventually cross over our event horizon. From our perspective, they will fade, stretched into invisibility by the redshift of their light. Billions of years from now, an observer standing on Earth, or whatever takes its place, may see only the nearest cluster of galaxies, with the rest of the cosmos erased from sight. The Milky Way and its local neighbors, bound together by gravity in a structure called the local group, will remain. So will the slightly larger Virgo cluster, perhaps, since its gravity is strong enough to resist expansion locally. But the great sprawl of galaxies beyond will have slipped away. The vast walls and filaments of the cosmic web that stretch across hundreds of millions of light years will dissolve into invisibility. In that distant future, astronomers might not even be able to tell that an expanding universe ever existed. Their observable horizon would be too limited to reveal the broader story. We live in a very special time in cosmic history. Right now, the universe is still young enough that we can see billions of galaxies stretching back almost to the beginning of time. This allows us to measure expansion, trace cosmic evolution, and uncover the deep story of how everything came to be. But in the far future, intelligent beings will not be so lucky. It is striking to think of how dependent our understanding of the cosmos is on the thin slice of the universe we can actually observe. Our maps of galaxies, our detection of supernovae, all of it comes from within our bubble of visibility. The universe beyond that bubble could hold countless wonders we will never know. Our cosmic archive is being erased line by line, page by page. Even though the universe itself may last for trillions of years, the accessible part, the part we can study and learn from, grows poorer with time. Some researchers even imagine using this fading to measure dark energy more precisely. By tracking how galaxies drift beyond the event horizon, we can learn how quickly expansion is accelerating. It becomes a kind of cosmic stopwatch. Each disappearing galaxy is not just a tragedy for the night sky, but also a data point in the greatest scientific puzzle of our age. The irony is sharp. We lose the galaxies themselves, but in their loss we find clues about the force that took them away. Change comes slowly, but it comes. Just as mountains erode and stars burn out, the visible universe itself is decaying, not in matter, but in meaning, shrinking the arena of what can be known. And perhaps that is the most humbling thought of all, that the cosmos, vast and ancient, is not only expanding, but also erasing itself from our view, until the stars we see tonight are the last sparks in an otherwise dark and silent sea. The edge illusion. Why the universe doesn't have a boundary. In our daily lives, everything has edges. A table has edges, a room has walls, even the Earth itself has a surface that can be circled and touched. Our imagination wants to extend that same logic to the cosmos. If galaxies, stars and planets fill the universe, then surely there must be a point where they stop, a frontier where space gives way to something else. Yet modern cosmology tells us that this picture is an illusion. The universe does not have an edge. Our instinct is to think that surely the universe must sit inside something bigger. But when cosmologists talk about the universe, they mean all of space and time. There is no external container. Asking what lies beyond the universe is a bit like asking what is north of the North Pole. It's not that it's hiding something, It's that the question itself stops making sense once you understand the geometry. In everyday life, we see straight lines as truly straight and parallel lines never meeting. But in the universe, large-scale geometry is determined by matter, energy, and expansion. Space can be curved in ways that are hard to picture. If the universe is closed, like the surface of a sphere, then traveling far enough in one direction might eventually bring you back where you started, without ever crossing an edge. If the universe is flat or open, it may stretch infinitely with no boundary at all. In either case, there is no wall where space abruptly stops, just a shape that continues on its own terms. This insight also reshapes how we think about the word infinite. An infinite universe is not infinite because it goes beyond a physical edge into something else, but because space itself simply has no limits. It continues, perhaps forever, in every direction. If it is finite, like a curved surface, it still has no boundary, only a repeating structure that loops back on itself. Both options dissolve the idea of an edge as a physical thing. What feels like an edge is just a limit of perspective. In fact, modern measurements of the CMB have provided clues that space is extremely close to flat, which hints at a potentially infinite structure. If this is true, then our observable universe, the 46 billion light-year sphere we can see, is only a tiny patch of a much larger, perhaps endless cosmos. There is no wall at the edge of that patch, just more space, more galaxies and more structures stretching beyond our reach. The shape of expansion, flat, open, or closed universes. In everyday life, we learn that the angles of a triangle add up to 180 degrees. On a flat sheet of paper, that is always true. But if you draw a triangle on the surface of a sphere, the rules change. Imagine connecting the North Pole to 2 points on the equator 90 degrees apart. You get a triangle with 3 right angles, 270 degrees in total. Space on a sphere is curved positively. On the other hand, if you try to draw a triangle on a saddle-shaped surface, the angles add up to less than 180. That is negative curvature. Flat, spherical, and saddle-like geometries are the simplest analogies for what cosmologists mean by flat, closed, or open universes. Gravity pulls matter together, but expansion pushes it apart. Which one wins depends on how much matter and energy the universe contains. If there is enough mass and energy, gravity slows expansion until it eventually reverses. In this case, the universe is closed. It curves like a sphere, finite but without an edge. If there is too little matter, expansion overcomes gravity and the universe is open. It curves like a saddle, expanding forever with no chance of collapse. And in between these two lies the flat universe, balanced precisely so that expansion continues forever, but only just so, with no eventual collapse and no rapid runaway. For much of the 20th century, astronomers did not know which of these 3 shapes matched reality. Observations could not yet measure cosmic geometry precisely, and different theories made different predictions. Some scientists leaned toward a closed universe, feeling that gravity's pull would eventually slow and reverse expansion. Others thought it might be open, destined to drift apart endlessly. The idea of a perfectly flat universe seemed too much of a coincidence. After all, why should the cosmos balance on a knife's edge between collapse and runaway expansion? But inflation theory shifted this thinking. Inflation smoothed and flattened everything like stretching out a wrinkled sheet. The result of this process would be a universe that looks flat on the largest scales. If inflation was correct, then flatness was not an unlikely accident, but an inevitable consequence of the universe's earliest moments. In the early 2000s, satellites from NASA and later the European Space Agency provided answers. They showed that the universe is astonishingly close to flat. Within experimental error, the geometry of space does not curve like a sphere or a saddle. It stretches on in a flat plane, balanced with remarkable precision. This was one of the strongest pieces of evidence supporting inflation. The precision of the measurements is staggering. The margin of error is so small that cosmologists can say with confidence that if the universe does have curvature, it is incredibly slight. So slight that the observable region would still look flat to us. The Earth is round, but your horizon looks flat. In the same way, the universe could be subtly curved on scales larger than we can observe, but appear flat from our vantage point. This leaves open a small but fascinating possibility that the cosmos could still be closed or open beyond what we can measure. For it to be so close to flat today, conditions in the early universe had to be fine-tuned to an almost impossible degree, unless inflation naturally smoothed things out. Without inflation, flatness would seem like a cosmic miracle. With inflation, it becomes the natural outcome of physics. This tension between coincidence and explanation drives much of the debate about cosmic shape. Some speculate that flatness may be an illusion tied to our limited perspective. Perhaps the larger cosmos beyond what we can observe curves dramatically, but we live in a region smoothed by inflation. In that case, our observable universe is just a patch, one among many in a far larger structure. Will everything collapse, drift apart, or continue balanced forever? And if it is so perfectly flat, what mechanism shaped it that way? Even now, with the best instruments humanity has built, we only see part of the picture. Our observations today point strongly towards flatness, but the deeper truth of cosmic shape may remain hidden, waiting for future science. The cosmic future of the Milky Way, moving into merger. In about 4.5 billion years, the Milky Way will collide with the Andromeda galaxy, its nearest large neighbor. While this may seem far off, the motion between the two galaxies is already set in motion. Despite the overall expansion of the universe pushing galaxies apart, the mutual gravitational attraction between the Milky Way and Andromeda is pulling them toward each other. This is an example of how gravity can override the effects of cosmic expansion when objects are sufficiently close together. The Milky Way and Andromeda are currently on a slow collision course. Both galaxies are moving toward one another at a speed of about 110 kilometers per second, which may sound fast, but considering the vast distances involved, it will take billions of years for the two to actually collide. In the process, both galaxies will begin to distort as they interact gravitationally, their shapes stretched and altered by tidal forces. As they approach one another, their mutual gravity will start to pull them closer, causing gas, stars, and dark matter to become tangled. This is where things get interesting because the collision will result in the merging of two galaxies into one. Though the idea of a galactic collision might conjure images of stars crashing into one another, the reality is more nuanced. Stars within the two galaxies are spaced so far apart that they won't collide directly. Instead, the galactic disks will pass through each other, their stars and other material interacting via gravity. Gas clouds will collide, triggering new star formation in certain regions, and in others, stars will be flung out into the vastness of space. The supermassive black holes at the centers of both galaxies will also play a crucial role in the event. As the galaxies merge, the two black holes will eventually sink toward the new center of the combined galaxy and spiral in toward one another. Over time, they will likely merge into one larger black hole. This merging event, known as a galactic collision, will have profound effects on the structure and dynamics of both galaxies. The two galactic disks, currently a collection of stars, gas, dust, and dark matter, will eventually combine to form an entirely new, likely elliptical galaxy. The collision will reshape the Milky Way, turning it into a new type of galaxy and change the motion of the stars and gas within it. Rather than orbiting in orderly circular patterns, stars will be scattered into more irregular orbits around the center of the new merged galaxy. Dark matter will influence the overall motion of the galaxies as they come together. Unlike the stars, which will interact and collide in various ways, dark matter will mostly pass through the other galaxy without much direct interaction. However, it will still exert its gravitational pull, shaping the overall structure of the merged galaxy. This means that even though we cannot see dark matter directly, Its effects on the motion of the galaxies will be crucial in determining the final outcome of the merger. This process of galactic collision and merger is a common event in the life cycle of galaxies. Over the course of the universe's history, galaxies have been merging and colliding regularly, with many galaxies today having a history of such interactions. These mergers can significantly alter the properties of the galaxies involved, including their size, shape, and star formation activity. For example, when smaller galaxies collide, their gas and stars are often compressed, leading to intense bursts of star formation, known as starbursts. This process can also trigger the growth of supermassive black holes as the gas and dust funnel toward the center of the galaxy. It's not just gravitational attraction that drives galactic mergers. The motion of gas and dust within galaxies also plays a crucial role in shaping the outcome of these collisions. As galaxies move closer to one another, their gas clouds begin to interact, often leading to the formation of new stars. This process, known as gas compression, occurs when the gas clouds in the two galaxies collide, causing them to become dense and triggering the birth of new stars. This can result in a starburst, which is often seen in merging galaxies. In some cases, these starbursts can last for millions or even billions of years, leading to the creation of thousands of new stars. The dynamics of the galaxies themselves can be altered in significant ways. The stars in the merged galaxy will no longer orbit in the familiar spiral pattern that we see in both the Milky Way and Andromeda today. Instead, their orbits will become more random, leading to a more elliptical shape. This transformation is not immediate, but will unfold over billions of years, as the gravitational interactions between the galaxies continue to reshape their structures. Even though the collision between the Milky Way and Andromeda will occur over a timescale of billions of years, it will have little impact on our immediate environment. The vast distances between stars mean that direct collisions between individual stars are unlikely. However, the gravitational forces at play during the merger will likely cause disruptions in the orbits of stars and planets. For example, the Sun and its planetary system might be flung into a different orbit, altering the conditions here on Earth. Over time, the collision could also trigger the formation of new stars in the galactic center, where intense gravitational forces compress gas and dust, creating the conditions for star formation. The Milky Way-Andromeda collision is just one example of how motion in the universe plays out on a smaller scale. While the expansion of the universe may be responsible for pushing galaxies apart on the largest scales, gravity remains the dominant force in galaxy clusters and smaller groupings of galaxies. The galaxies in the local group are moving toward one another due to their gravitational attraction, and eventually they will merge in a process similar to what will happen between the Milky Way and Andromeda. If expansion slows, the Big Crunch scenario. Instead of an endless flight outward, the cosmos could one day turn inward, collapsing in a final act that mirrors the beginning. To understand the Big Crunch, we have to return to the tug-of-war that shapes the universe. On one side is the momentum of the Big Bang, which sent space flying outward nearly 14 billion years ago. On the other is gravity, the universal force that pulls matter together. The expansion of the universe is not like a ball thrown through the air with no resistance. Instead, it is like a ball thrown upward, slowed by Earth's pull. If the ball is thrown fast enough, it will escape gravity and never return. If not, it will rise for a while before eventually falling back down. The fate of the universe depends on which side of this cosmic struggle has the final word. In the decades before the discovery of dark energy, many believed the Big Crunch was the most natural end. This collapse would not be gentle. Over billions of years, the great clusters of galaxies would be drawn inward. Galaxies would smash together, stars would collide, and enormous black holes might merge into titanic objects. Heat and energy would rise as everything compressed. The entire universe would shrink, growing hotter and denser with each step. At the end, the cosmos might reach a state that resembles its birth. All of space squeezed into a single, unimaginable point of energy and density. The Big Crunch offers a strange kind of symmetry. If the universe began with an explosion of expansion, then perhaps it will end with a crash of contraction. If everything compressed into a single point, perhaps it would once again explode outward in a fresh Big Bang, birthing a new universe. But while the idea is beautiful, evidence has pushed it further from the center of scientific thought. If dark energy continues to dominate, the universe will not fall back inward. Still, the Big Crunch has not been completely dismissed. One reason is that dark energy itself remains a mystery. This opens the door for contraction. The future depends not just on what dark energy is now, but on how it behaves over unimaginable timescales. If a Big Crunch were to happen, the process would unfold on scales of billions or trillions of years. It would begin almost unnoticed, with the expansion of galaxies slowing ever so slightly. Over time, the distance between galaxies would stop growing and instead start shrinking. Entire galactic superclusters would drift back together. The night sky, instead of thinning into emptiness, would grow brighter as galaxies crowded in. Eventually, collisions would become common. The Milky Way might crash into its neighbors not only once but many times as everything converged. The stars themselves would not survive forever in such a universe. Many would burn out during the long ages of collapse. Others would smash into each other, igniting bursts of new stars, only for those too to burn out quickly. Black holes, already among the most extreme objects in the cosmos, would play an even bigger role in the contracting universe. As matter clumped together, black holes would merge, becoming giants that swallowed entire galaxies. In the end, these black holes themselves might be swallowed by the collapsing fabric of space. As the collapse continued, temperatures across the universe would rise. Unlike today's universe, which cools as it expands, a contracting cosmos would heat up as everything compressed. Radiation would intensify, energy would grow denser, and space itself would glow with unbearable fire. The very fabric of space-time would fold inward until it reached a final point of destruction. Whether this end would be a smooth compression into a single point or a violent chaotic collapse is uncertain. In either case, the universe as we know it would cease to exist. For human beings who live on such a short timescale, the prospect is both terrifying and strangely calming. The end would not come tomorrow, or even in the lifespan of our species. It would be written into the far, far future, unfolding over cosmic ages so long they dwarf all of human history. Could expansion be an emergent illusion? The idea that space-time might not be the foundation of reality is part of a broader class of theories that challenge our conventional understanding of the universe. One of the most intriguing of these ideas is the notion of emergent space-time, which suggests that space-time, along with the expansion of the universe, could arise from more basic, underlying phenomena. In an emergent framework, space-time could be a large-scale phenomenon that emerges from the collective behavior of fundamental quantum processes. Rather than being an intrinsic feature of the universe, space-time would be the result of interactions between quantum objects, like entangled particles. This would imply that everything we perceive as the fabric of space-time, the vast distances between galaxies, the stretching of space and the very passage of time, could be a byproduct of something deeper and more fundamental. To understand this, it helps to first grasp what we mean by emergence in physics. Emergent properties are features of a system that arise when the system as a whole behaves in a way that cannot be directly explained by its individual parts. For example, the wetness of water is an emergent property. While individual water molecules are not wet, when they interact in large numbers, their collective behavior gives rise to the sensation of wetness. Similarly, in physics, the concept of emergent phenomena has been used to explain complex behaviors that arise from simpler interactions, such as how the behavior of a gas can be explained by the motion of individual molecules, or how the properties of a liquid can arise from the interactions of its molecules. In the context of the universe, the idea of emergent spacetime suggests that the large-scale structure of the cosmos, including the expansion of space, could emerge from quantum entanglement or other quantum phenomena. Instead of spacetime being a fundamental background against which all events unfold, it might be a large-scale illusion created by the interactions of smaller, more basic entities. The expansion of the universe, for example, might not be a feature of spacetime itself, but rather a consequence of the way quantum processes unfold on a cosmic scale. One theory that touches on this concept is the idea of holography. According to the holographic principle, the three-dimensional world we perceive could be a projection of information stored on a two-dimensional surface, much like a hologram. This principle was inspired by the study of black holes, where researchers found that the amount of information within a black hole seems to be proportional to the area of its surface, rather than its volume. In this view, the universe itself might be a kind of hologram, with our experience of space and time arising from two-dimensional information encoded at the boundaries of the cosmos. Taking this concept a step further, some physicists argue that space-time, rather than being fundamental, might also be an emergent property, one that arises from deeper quantum processes. In the context of emergent spacetime, it's suggested that quantum entanglement might be responsible for the creation of the very structure of space and time. If entangled particles can influence each other instantaneously, it might be possible that large-scale cosmic phenomena, like the expansion of the universe, emerge from the entangled relationships between quantum objects. In this scenario, the entire cosmos, including the motion of galaxies and the stretching of space, might be a result of quantum entanglement and other fundamental processes that operate on scales far smaller than we can directly observe. If spacetime is emergent, the very idea of expansion could be reinterpreted. Instead of imagining galaxies moving apart through space, we might need to think of them as part of a more complex, interconnected quantum web. The space between galaxies wouldn't be stretching, but rather the effects of quantum processes at a fundamental level that give rise to the perception of expansion. This could also imply that the fabric of space is not a smooth, continuous entity, but a result of quantum events happening at the smallest scales. In the classical view of the universe, time is a continuous, linear progression. 1 second follows another, and we experience the passage of time as a steady flow. But if time is an emergent property, what does it mean for the passage of time? Could time be a consequence of the way quantum particles interact with each other? If so, what would it mean for our experience of time on the human scale, where the passage of time feels continuous and uniform? Emergent spacetime theories also lead to questions about the ultimate fate of the universe. If the expansion of the universe is just a side effect of quantum processes, could the nature of this expansion change as we gain a deeper understanding of the underlying mechanics? Could the rate of expansion slow down or speed up based on shifts in quantum interactions? What happens if the fundamental quantum processes that give rise to space-time undergo a shift or transformation? These questions are at the forefront of modern theoretical physics and offer tantalizing glimpses into the unknown. Perhaps most intriguingly, the idea of emergent spacetime challenges our perception of the universe. Instead of viewing the universe as a vast, immutable entity governed by fixed laws of physics, this theory suggests that the universe is an intricate, dynamic process constantly evolving. What we perceive as space and time could be the result of interactions that might stretch back to the beginning of the cosmos, when the first quantum events began to unfold. In the coming years, as we continue to probe the nature of reality using both theoretical models and experimental techniques, we may discover that the expansion of the universe is not a simple stretching of space, but a profound signal of deeper processes at work. If spacetime is not fundamental, but emerges from more basic principles, then the expansion of the universe might be a clue that we are on the verge of understanding a much larger, more mysterious reality. A perfect balance, the cosmic big freeze. Imagine the universe as a great ocean, waves spreading outward in every direction. In the early days of the cosmos, that ocean was turbulent and crowded, filled with storms of matter and radiation. Galaxies swirled together, stars were born in brilliant clusters, and the universe was alive with energy. But over time, as expansion carried galaxies farther and farther from each other, the cosmic waters began to calm. The idea of the Big Freeze takes this picture to its ultimate conclusion. The Big Freeze scenario is sometimes confused with heat death, but they are not exactly the same. Heat death is tied to the spread of energy and entropy, the inevitable process where usable energy runs out. The Big Freeze, however, focuses more on the steady pace of expansion itself. In this vision, the universe does not accelerate uncontrollably, nor does it collapse back on itself. Instead, it continues coasting outward in balance, a quiet rhythm that stretches galaxies apart without any dramatic upheaval. At first glance, this may sound like a peaceful end, but in truth, it is one of the loneliest futures one can imagine. To understand why, consider the galaxies we see today. They are bound into clusters woven together by gravity. Our Milky Way is part of the local group, a small family of galaxies bound tightly enough that they will not drift apart even as space grows. In the Big Freeze, these clusters remain intact, but everything beyond them slips farther and farther away. The stars of other galaxies will be lost forever. Inside each surviving cluster, the story continues at a smaller scale. Stars will live out their lifespans, some exploding as supernovae, others quietly burning until their fuel runs dry. For billions of years, new stars will still form, recycling gas and dust into fresh bursts of brilliance. But the raw material will not last forever. Eventually, gas clouds will thin and fewer stars will be born. The galaxies will begin to dim. As time stretches further, the population of stars changes. Bright, massive stars disappear first, their short lives ending in spectacular explosions. Medium stars like the Sun live longer, shining steadily for billions of years before turning into white dwarfs. In the far reaches of time, most of the remaining stars will be small, cool red dwarfs. These faint stars burn so slowly that they can last for trillions of years, far longer than the universe has existed so far. In a Big Freeze future, the red dwarfs will outlast nearly everything else, tiny flickers of warmth in a universe that grows darker with each passing age. Yet even these hardy stars will eventually fade. White dwarfs, neutron stars, and black holes will dominate the cosmic landscape. Galaxies will no longer sparkle with billions of shining suns. Instead, they will be filled with dead remnants, quietly orbiting in the dark. For a long while, occasional collisions might still spark new events, stars merging, black holes devouring unlucky companions, but these will become rare. The fireworks of the cosmos will slow to almost nothing. Temperature plays a key role in this vision. As space expands, the leftover radiation from the Big Bang continues to stretch and cool. Today, the universe is filled with the CMB. In the Big Freeze scenario, this radiation keeps thinning and cooling until it becomes so weak that it is practically non-existent. Every part of the universe drifts toward the same fate, a state of nearly perfect cold, where energy is too thinly spread to spark new activity. It is neither the violence of a big crunch, collapsing everything into fire, nor the chaotic shredding of a big rip, tearing atoms apart. It is expansion that never stops but also never rushes beyond control. A universe that slowly, almost gently, empties itself out. In a sense, it is the simplest outcome. Nothing dramatic happens, nothing sudden changes, and yet step by step, the cosmos transforms into a place where activity is impossible. From our human perspective, stars, galaxies, and even the universe seem eternal because they live far longer than we do. But the Big Freeze asks us to think on scales beyond trillions of years. In that distant future, galaxies we see now will be gone from sight, stars will no longer form, and only dark remnants will remain. The universe will not end in a dramatic event. Instead, it will simply continue on, colder and quieter, until change itself becomes rare. Imagine a night sky with no Milky Way, no galaxies, no clusters beyond our own. Imagine stars growing fewer and fewer until only faint red glimmers are left. Imagine those too winking out, leaving only black holes and frozen remnants drifting in silence. Over unimaginable spans of time, even black holes might evaporate through processes like Hawking radiation, leaving behind only particles spread thin across endless space. If the universe's acceleration slows and balances, this quiet fate becomes likely. For the universe, this fading would take far longer than we can easily imagine. Yet no matter how long it takes, the final picture is the same: a cosmos without light. The black hole era, a universe where only darkness remains in motion. In the farthest reaches of time, when the stars are gone, when galaxies have dissolved into cold emptiness, and when nearly every trace of the vibrant cosmos has slipped into silence, only black holes will remain. They are the most enduring engines of gravity, the ultimate survivors of a universe that has otherwise gone still. While stars live for billions or trillions of years, black holes stretch their influence across scales of time so vast that human imagination can barely grasp them. It is here, in this unimaginably distant future, that the black hole era unfolds. A cosmos where darkness itself is the final keeper of energy, slowly whispering away into nothing. Over the long ages of cosmic history, as stars exhaust themselves and galaxies fall apart, black holes become the last reservoirs of structure. They do not shine like stars, and they do not orbit one another in grand galactic spirals. Instead, they sit in the dark, patient, waiting, as the universe grows colder and emptier around them. At first, these black holes will exist within the remnants of galaxies. Even after stars are gone, the central black holes of galaxies remain, each one carrying the mass of millions or billions of suns. Smaller stellar mass black holes, born from collapsed stars, drift silently through the dark, scattered across the void. If two black holes meet, their immense gravity pulls them together and they merge in a titanic collision. These rare but powerful events produce gravitational waves, but even those waves eventually fade as the universe stretches, their energy diluted across growing space. What is left is silence again, broken only by the slow, patient transformation of black holes themselves. For a long time, black holes were thought to be eternal. They seemed like ultimate prisons of matter, swallowing everything that crossed their event horizons and never letting anything out. But in the 1970s, Stephen Hawking proposed the idea that black holes are not completely black. Thanks to the strange rules of quantum mechanics, tiny fluctuations near the edge of a black hole, the event horizon, allow energy to leak out in the form of faint radiation. This became known as Hawking radiation. And if Hawking was correct, then even the most massive black holes are not permanent. They slowly evaporate, losing mass bit by bit until nothing remains. The timescales for this evaporation are staggering. A black hole as massive as a star could take around 10 to the power of 67 years to evaporate. A number so large, it makes the current age of the universe seem like the blink of an eye. For supermassive black holes, the kind at the centers of galaxies, the timescales are even greater, up to 10 to the power of 100 years or more. These numbers are almost meaningless to us because they lie so far outside any human or even stellar timescale. Yet in the deep future, when nothing else is left, this will be the last process of change in the cosmos. The universe will be silent, but not completely frozen. Black holes will still be evaporating, slowly shrinking, glowing faintly with radiation as they dissolve into nothingness. This process is not dramatic, at least not at first. The radiation is faint, far too weak to notice in the young universe we live in now. But as a black hole loses mass, the process speeds up. In its final moments, a black hole radiates furiously, becoming brighter and hotter until, in a burst of energy, it disappears completely. For small black holes, this final explosion could be immense, like a last firework in the darkness. For the giant ones, it is more like a long, slow burn, ending with a whisper rather than a bang. Yet no matter the size, the end result is the same: emptiness, the last echo of matter released into a universe that has little left to receive it. The black holes represent the last bastions of motion, gravity, and transformation in a cosmos that is otherwise at rest. After even atoms themselves may decay, black holes stand as the final players on the stage. They are the guardians of time, stretching the story of the universe into epochs so vast that even eternity feels too short a word. Our sun will live another 5 billion years. The galaxy will endure for trillions. But the black hole era stretches beyond all of that. Black holes, once thought to be destroyers, turn out to be the last givers. They return their energy to the universe, releasing it in the slowest, most delicate trickle of radiation imaginable. The heat death of the universe, motion with no purpose. Entropy is often described as disorder, but a better way to think of it is as the spreading out of energy. When energy is concentrated, it can do work. A lump of coal can burn, a battery can power a light, a star can shine. But when energy is spread out evenly, like warm air filling a room, there is nothing left to extract. It has no gradients, no differences to exploit. In physics, all useful processes, from life to machines to the very shining of the sun, depend on such gradients. Once they are gone, once energy is evenly distributed everywhere, motion may continue, but it becomes pointless. This is the essence of heat death. It is not that atoms stop vibrating or that particles stop moving. It is that their movement ceases to matter because nothing can be done with it. A wind blowing across a desert has energy you can use, but if every single atom of air in the desert were moving at random in every direction, with no difference in temperature, pressure, or speed, the result would be useless chaos. There would be motion, but no purpose. That is the vision of the universe at heat death. To see how we get there, we need to trace the universe's history in terms of entropy. At the Big Bang, entropy was surprisingly low. Despite the extreme heat and density, the universe was very uniform, which may sound like high entropy, but in terms of gravitational structure, it was actually a state of remarkable order. As time passed, entropy increased, stars formed, galaxies grew, and planets took shape. All of these structures are the result of energy differences being exploited, gas clouds collapsing under gravity, nuclear fusion igniting in dense cores, radiation pouring outward into colder space. Each of these steps increased entropy, like water flowing downhill. Even now, entropy is increasing all around us. The sun is constantly losing its usable energy as it spreads photons across the cosmos. Every chemical reaction, every heartbeat, every storm on every planet adds to the total. The second law of thermodynamics, the rule that entropy never decreases overall, is relentless. The universe is like a great bank account that can only ever spend, never save. Eventually, the balance will reach zero. What does this look like on cosmic scales? First, stars will burn out. At that point, the only sources of energy will be the slow decays of matter and the evaporation of black holes. But even these final sparks of activity will one day fade. When the last black hole evaporates, the universe will be left with a thin bath of low-energy particles, photons, neutrinos, and perhaps the lightest remnants of matter. These will fly endlessly through space, rarely colliding, never forming anything new. The universe will not be dead in the sense of being static, because motion will still exist. But it will be a motion without contrast, without gradients, without change in the way we understand it. This is the key distinction. In the heat death scenario, the universe doesn't freeze solid like a block of ice. Instead, it becomes a lukewarm fog spread evenly across infinite space. Every part of it looks like every other part. Time itself seems to lose meaning, because time is marked by change, and change depends on differences. Without differences, nothing distinguishes one moment from another. For some, this picture is profoundly unsettling. It means that no matter what happens, whether civilizations rise and fall, whether galaxies are born and destroyed, whether black holes consume everything or not, the end state is the same. It is unavoidable, written into the mathematics of entropy. And yet, it is worth asking, is this truly the only way the story can end? Some physicists argue that heat death depends on assumptions about dark energy and the structure of the universe that may not hold forever. Others speculate that quantum effects, rare fluctuations, or even entirely new laws might reset the game. But as far as current science can tell, entropy only increases and the heat death is the natural result. One way to think about it is to compare it to the life of a star. A star spends most of its life burning bright, releasing energy, driving processes that shape its surroundings. But eventually, it runs out of fuel. It cools, it collapses, it may explode, but in the end, it is reduced to something much simpler. The universe is like that star, just on a grander scale. It began hot, bright, and full of potential. It spent billions of years creating galaxies, planets, and life. And it will end not in fire, but in quiet equilibrium. The phrase "motion with no purpose" captures the tragedy of heat death. The universe will still hum with the jitter of particles, but none of it will ever matter again. In this state, eternity stretches out as a blank canvas that nothing will ever paint upon again. Cycles and rebounds, the Big Bounce alternative. It is tempting to imagine the universe as a one-way journey, a beginning in the Big Bang, an expansion across billions of years, and eventually an end in one of the scenarios scientists debate. But not everyone is satisfied with a universe that has a single start and a final conclusion. Instead, some scientists have wondered if the cosmos could be part of a cycle, collapsing, bouncing, and expanding again, perhaps endlessly. This idea is known as the Big Bounce, and it challenges one of the most basic assumptions we carry, that the universe must have a single origin and a single fate. If the universe can expand, then what would stop it from eventually reversing? If expansion slowed and everything fell back inward, collapsing into a dense state, would that be the end, or could something new begin? Could the same physics that allowed the Big Bang to start expansion in the first place also restart it after a collapse? One of the oldest versions of this idea came from the notion of a closed universe, shaped like a sphere. In such a model, space is curved back on itself. Expansion might continue for a long time, but eventually gravity would halt it and everything would collapse in. But instead of ending there, some versions of the theory suggest that the collapse would not settle into a permanent point of infinite density. Instead, the collapsing matter and energy might rebound, igniting a new expansion, a new Big Bang. This cycle could, in theory, happen over and over again. Each expansion leads to a collapse, and each collapse leads to another expansion. The universe, in this view, would be eternal, without a true beginning and without a final end. It would be a cosmic heartbeat, pulsing forever between growth and contraction. For many, this is an appealing picture. Of course, the physics of such a rebound is not simple. At the point of collapse, matter would be compressed into unimaginable densities. Under Einstein's equations, such a situation tends to lead to a singularity. But some physicists suggest that quantum mechanics could prevent a singularity from forming. Instead of a final breakdown, quantum rules might force a bounce, creating the seed for expansion to begin again. This is where theories of quantum gravity come in. Ordinary relativity works well on large scales, while quantum mechanics rules the small. But at the extreme densities of a universe collapsing to its minimum, both must apply at once. Some proposals, such as loop quantum cosmology, attempt to merge these ideas. In these models, space itself is not smooth and continuous, but made up of tiny, discrete units. When the universe compresses to its smallest size, the granularity of space resists further collapse, creating a rebound. Expansion then resumes, leading to another era of galaxies, stars, and cosmic evolution. If this were true, then perhaps the universe we inhabit today is not the first. There could have been cycles before us, each with its own stars, galaxies, and even the possibility of life. Each bounce would wipe away most evidence of the last cycle, leaving behind only subtle imprints in the CMB or in the deep structure of spacetime. People have looked for such imprints, patterns in the leftover light from the early universe that might hint at a prior cycle. So far, the results are uncertain, but the idea keeps drawing attention because of how neatly it reshapes the story of cosmic history. The Big Bounce raises questions about entropy. In the standard picture, entropy always increases. That's part of why scenarios like heat death are so convincing. But in a bouncing universe, what happens to entropy? If each cycle simply carried forward the entropy from the last, then disorder would keep building endlessly, making each new universe more diluted and chaotic than the last. Some versions of bounce theory tackle this by suggesting that entropy resets in each collapse, perhaps through certain unknown mechanisms. If the Big Bounce is real, then the universe does not need a beginning in the traditional sense. It was never created from nothing. It has simply always been, moving through cycles of birth, death, and rebirth. Observations today show that the universe's expansion is not slowing down. If this acceleration continues forever, a bounce may never occur. For a bounce to happen, dark energy would either need to fade or change its nature. Not impossible, but it remains highly uncertain. The Big Bounce also depends on assumptions about what happens in extreme conditions we cannot yet test. Quantum gravity, loop models, and other approaches are still highly theoretical. No telescope has yet seen clear evidence of a prior cycle, though some researchers claim there might be hints. Without direct proof, the Big Bounce remains a beautiful possibility, an alternative way of thinking about cosmic time that has not yet been confirmed. The Little Rip and Pseudo-Rip models. The idea of the universe tearing itself apart is often painted in violent images, with galaxies ripped apart in sudden catastrophic ways. That is the picture of the so-called Big Rip. But there are softer versions of this idea, more subtle in their unfolding, where instead of a single dramatic ending, the universe slowly loses its structure and coherence. These are the Little Rip and Pseudo-Rip models, and they describe a cosmos that does not explode apart in one instant, but instead unravels bit by bit, like threads slipping from an old fabric. In the Big Rip picture, dark energy keeps growing stronger and stronger, eventually breaking apart galaxies, stars, planets, and finally even atoms. But in the Little Rip and Pseudo-Rip versions, dark energy does not necessarily explode into infinity. Instead, it either grows steadily without limit, or reaches a fixed strength just shy of total destruction. The Little Rip is the first of these ideas. Here, the force of dark energy never reaches a final endpoint where it becomes infinite, but it keeps increasing over time. The key is that its growth is slow, almost gentle. Galaxies that are bound together today would eventually lose their grip on each other, but not in a sudden blast. Over billions or even trillions of years, the pull of dark energy would stretch them apart, like a tide that keeps rising higher and higher. Stars bound to galaxies would eventually drift away. Planets would leave their stars. Atoms themselves might not be torn apart in one instant, but given enough time, even the smallest bonds would weaken under the slow, steady push. The Little Rip is less of an explosion and more of a cosmic unraveling, where the universe simply fails to hold itself together. The Pseudo-Rip is a bit different. In this picture, dark energy grows stronger, but not without limit. It approaches a fixed strength, strong enough to tear apart galaxies or clusters of galaxies, but perhaps not strong enough to destroy stars or atoms. Imagine a hand slowly squeezing, then stopping once the grip is firm, without crushing everything inside. In this case, certain cosmic structures would break apart, while others might remain intact forever. For instance, galaxies might scatter apart from one another, but stars within a galaxy might stay bound. Or planetary systems might remain orbiting their stars, even as those stars drift into an increasingly empty and lonely universe. The Little Rip and the Pseudo-Rip suggest endings that are not absolute in the dramatic sense, but are instead gradual. The Little Rip predicts a universe where eventually, given enough time, no bond can resist the slow but endless stretching of space. The Pseudo-Rip leaves a universe where some structures survive, drifting endlessly in a diluted void. Both are quieter visions compared to the fiery image of the Big Rip or the violent collapse of the Big Crunch. They are stories of gentle endings, of slow separations, and of decay rather than explosion. These models also highlight how delicate the balance of dark energy really is. If its strength grows without limit, even slowly, then no force can stand against it. But if it approaches a fixed strength, the outcome depends on where that final value sits. Just a small difference could decide whether stars are torn apart or remain whole, whether planets continue orbiting or drift free. This shows how sensitive the universe's destiny is to the exact nature of dark energy, a mystery we are only beginning to measure with telescopes and observations. In the Little Rip, the universe never experiences a clear final moment. There is no big ending, no sudden death. Instead, the story goes on endlessly, with structures dissolving one after another, in a timeline so long that the lifespans of stars look short by comparison. The pseudo-rip is equally strange, because it leaves behind an eternal universe that is both empty and not completely destroyed. Islands of stability could float forever in a vast ocean of nothing, perhaps leaving open the question of whether new physics might someday awaken them again. What does it mean for the universe to end if there is no final boundary, no sudden collapse or explosion? In the Little Rip, the ending is stretched into infinity, with no single moment to mark the death of the cosmos. In the pseudo-rip, the ending is partial, leaving behind pieces of order in a sea of disorder. Both challenge our sense of finality. Could motion point toward a deeper reality? The universe, with all its galaxies, stars and planets, seems like a vast and isolated system, governed by its own set of laws. But what if the motion we observe in the cosmos is not the entire story? What if the expansion of the universe is not just the unfolding of space itself, but a clue that points toward a much deeper and grander reality, one that lies beyond the boundaries of what we can see and understand? Motion, in the cosmic sense, has long been a critical aspect of our understanding of the universe. It has been observed in countless forms: galaxies moving away from each other due to the expansion of space, stars orbiting black holes and planets spinning around their suns. On the largest scales, the very stretching of space between galaxies suggests that the universe itself is constantly changing, always on the move. For many, this motion represents the whole story. The universe is expanding, and everything within it is being carried along by that expansion. But this picture might only be a surface-level interpretation of a much deeper truth. What if motion itself is a sign of something beyond the visible universe? Rather than just a result of the universe's expansion, could this motion be evidence of hidden dimensions, alternate realities, or deeper laws of nature? This idea is a core element of some of the most advanced theories in physics, particularly those concerning higher dimensions and the nature of reality itself. One of the most intriguing concepts in modern physics is the idea of extra dimensions, dimensions beyond the three spatial ones we experience every day. In the 20th century, relativity showed us that space and time are interconnected, forming a fabric that can be warped and stretched. But more recent theories, such as string theory and the concept of a multiverse, suggest that this fabric could be part of something even larger. According to these theories, the universe we observe may be just one slice of a much broader reality, and the motion of galaxies and the expansion of space could be an indicator of the existence of additional dimensions that we cannot directly perceive. String theory, for example, proposes that the fundamental particles of the universe, things like electrons and quarks, are not point-like objects, but rather tiny vibrating strings. These strings exist in multiple dimensions, some of which may be too small for us to detect. According to this theory, the universe we see may only be a three-dimensional projection of a much larger, higher-dimensional space. The motion of galaxies and the stretching of space could be clues to the existence of these hidden dimensions, which we are unable to directly observe. If this is true, then the motion we see in the universe might be a byproduct of something much larger at play, a deeper reality that exists beyond our sensory capabilities. The idea of hidden dimensions is not confined to string theory alone. Other theories, such as those involving parallel universes or the multiverse, also suggest that our universe might be just one of many. These parallel universes could exist in separate, unseen dimensions with their own sets of physical laws and constants. If the universe we observe is part of a greater multiverse, then the motion of galaxies and the expansion of space might not be the result of some isolated event like the Big Bang, but instead a reflection of larger, more intricate processes that involve multiple universes interacting with one another. Motion, in this sense, might not just be a feature of our universe, but a sign of its interconnectedness with other realities that exist beyond our ability to detect them. There are also deeper, more fundamental questions that the motion of the universe raises. For instance, some scientists speculate that dark energy could be a manifestation of a deeper law of nature, one that operates beyond the framework of our current understanding of physics. If motion is the result of these deeper laws, then the acceleration of expansion might be a clue that points toward forces or dimensions that lie beyond the observable universe. The fact that motion exists in the first place could be evidence of a deeper reality. On a fundamental level, the universe's expansion implies that space itself is not static. It's stretching and growing, and this motion has consequences for the galaxies and objects within it. The fact that the expansion is uniform across the universe suggests that something is driving this process at the most basic level. But what is this force, and why does it exist? Could it be that the motion of the universe is a reflection of some universal principle? A principle that governs not just our universe, but the entire multiverse? As we push the boundaries of scientific inquiry, we're confronted with questions that go beyond what we can measure with our current tools. These observations might be like looking at the surface of the ocean without realizing that there are currents below, shaping the flow of water in ways we can't perceive. The motion we see in the universe could be the result of forces or principles that lie beyond our current grasp, waiting to be discovered. In some ways, the motion we observe might be the key to unlocking the deepest mysteries of the universe. Rather than seeing it as a final answer, we could view it as a signpost pointing us towards something much greater. If the universe's expansion is just a clue, then what does it reveal about the deeper nature of reality? The idea that motion could be a gateway to understanding deeper realities opens up a wealth of possibilities. Consider the possibility that the motion we observe in the universe is not just a result of forces acting on objects, but a direct reflection of the way the universe interacts with a deeper, underlying structure. Perhaps spacetime is a kind of medium, a surface upon which higher dimensional processes play out. This could mean that the motion we see in the universe might be the visible manifestation of a deeper set of dynamics. Vacuum decay, a moving universe that ends suddenly. The concept of vacuum decay comes from quantum theory, and it suggests that the fabric of spacetime, the vacuum itself, may not be as stable as we think. In the most extreme version of this theory, the universe could collapse into a lower energy state, causing the laws of physics to change in a flash and rewriting the nature of existence in the blink of an eye. Quantum theory tells us that empty space is not truly empty. It is filled with fleeting quantum fluctuations, where particles constantly pop in and out of existence. These fluctuations give rise to what is known as the vacuum state, the lowest possible energy state in the universe. Quantum mechanics suggests that this vacuum state is not necessarily stable. Instead, it could be metastable, meaning that while it is stable for a long period, it could eventually decay into a lower energy state. This is similar to how a ball might sit at the top of a hill, balanced precariously, only to suddenly roll down to the bottom. If the vacuum were to decay, the laws of physics as we know them would change. The constants of nature, like the speed of light or the strength of gravity, could shift, and the structure of spacetime itself could be altered. In essence, the universe could end, not with a bang or a whimper, but with a sudden total transformation. To understand how this could happen, we need to dive into the nature of quantum fluctuations. At the quantum level, particles are constantly being created and destroyed in what's called a quantum field. This field is the most fundamental layer of reality, the stage upon which all particles and forces play out. The vacuum, then, is not empty, but rather filled with these tiny, ephemeral fluctuations that momentarily create particles before they vanish again. The vacuum state is the lowest energy state that the field can be in, but it is not necessarily the only possible state. There could be other, lower energy configurations that the universe might fall into, just as a ball can roll to a lower point on a hill. If this lower energy state exists, the transition to it could be catastrophic. When a bubble of this lower energy vacuum forms, it would expand outward at the speed of light, altering the very structure of spacetime and reality. Everything within this bubble would be rewritten, with the laws of physics changing in ways that are difficult to predict. It's as if the universe would be rebooted, with a new set of rules replacing the old ones. This concept of vacuum decay is tied to the theory of the false vacuum. The false vacuum is a theoretical state that the universe could currently be in, one that is not truly stable, but could persist for a long time. It's a kind of waiting room for a transition to a more stable state, which is the true vacuum. The idea is that if the universe is in a false vacuum, it could persist indefinitely without any noticeable changes. However, quantum fluctuations could eventually trigger a decay, causing the universe to collapse into a new vacuum state. This is something that would happen billions or even trillions of years from now if it were to happen at all. But the implications of vacuum decay are profound. If the vacuum were to decay, it would essentially mark the end of everything as we know it. All processes in the universe, from the movement of galaxies to the functioning of atoms, would cease to operate. In this sense, the universe would end, not by expanding and cooling into darkness, as other theories suggest, but by a sudden and absolute change in the very fabric of existence. The possibility of vacuum decay is not just an abstract idea, it is rooted in the principles of quantum field theory. The fact that the vacuum can exist in different energy states means that there is always the potential for such a transition. But just because it is possible doesn't mean it's likely. Most scientists think that if the universe is in a false vacuum, it is currently in a very stable state, one that could last for a long time before any decay occurs. However, there's still uncertainty. We do not fully understand the nature of the vacuum or the conditions that would trigger such a transition. The energy differences between a false vacuum and a true vacuum may be minuscule, but the consequences of a collapse are enormous. The discovery of vacuum decay, if it were to happen, would be hidden from our direct view, at least for a time. The bubble of lower energy vacuum would expand at the speed of light, meaning that nothing inside the bubble would know what was happening until it was too late. From our perspective, it would seem like the universe would simply cease to exist, with the laws of physics changing instantaneously. There would be no warning, no precursor. It would be as if the entire universe underwent a reset, starting fresh with a new set of rules and a completely different form of existence. In some sense, the idea of vacuum decay suggests that the universe might not be as permanent as we like to think. Even though the universe has existed for billions of years, it might not be immune to change. The laws of physics that have governed the cosmos from the moment of the Big Bang could be fragile, subject to shifts in the underlying vacuum state. At the smallest scales, reality is not as we perceive it. Particles flicker in and out of existence, and the fabric of space-time itself can warp and bend in unexpected ways. The concept of vacuum decay is a consequence of this strangeness, where even the vacuum itself is not stable, but is subject to the whims of quantum fluctuations. For now, vacuum decay remains a theoretical concept, and there is no evidence that it will occur anytime soon. In fact, the universe might be perfectly stable, with no sign of any transition to a true vacuum. But the universe is not as simple as it appears. Even the vacuum, the very fabric of existence, may harbor hidden dangers, capable of rewriting reality in an instant. It's a humbling thought, a reminder that even in a universe as vast as ours, the rules of existence are fragile, and everything we know could change in a heartbeat. Do laws of physics themselves evolve with expansion? The laws of physics as we understand them form the bedrock of the universe. For centuries, We've assumed that these laws are immutable, set in stone since the moment of creation. But what if this stability is an illusion? Could the very rules that govern the cosmos be subject to change over time, evolving as the universe expands? Some theories suggest that as space itself grows, the fundamental constants of nature might shift. If true, this would dramatically alter our understanding of the universe and the foundations of physics. The laws of physics are based on a series of numbers that don't change, regardless of where you are or when you measure them. For example, the speed of light in a vacuum is a constant, denoted by c. Similarly, the gravitational constant, which measures the strength of gravity, is another key figure. These constants allow scientists to predict how objects will behave in different environments. But what if, over time, these constants were not fixed? One theory that addresses this possibility is known as the varying constants hypothesis. It proposes that as the universe expands, the fundamental constants of nature might change, either gradually or more dramatically. For instance, the strength of the electromagnetic force might have been different in the early universe, affecting the formation of atoms and molecules. Similarly, gravity could have been stronger or weaker in the past, influencing the way galaxies and stars formed. These shifts might not be large enough to notice in our everyday lives, but they could have profound implications for the evolution of the universe. The idea that physical laws might evolve with cosmic expansion challenges the very notion of constancy in nature. It suggests that what we see today might not be the same as what existed in the past, or even what will be true in the future. In fact, some scientists think that the constants we measure now could continue to change as the universe expands. This raises the possibility that, over billions of years, the universe could gradually shift in ways that we cannot predict. One of the most famous examples of this concept involves the fine structure constant, a number that describes the strength of electromagnetic interactions. If this constant were to change over time, it would have profound effects on chemistry and the structure of atoms. The properties of elements could shift, and life as we know it might not even be possible. The same could be said for the strength of gravity, which governs the motion of planets and stars. If gravity had been weaker in the early universe, galaxies and stars might not have formed in the way we see today. If it had been stronger, the universe might have collapsed under its own weight. But how do we know if these constants have changed? One way to investigate is by looking at the light emitted by distant objects, such as quasars and galaxies. Light travels across space at a constant speed, but as it travels through the expanding universe, it stretches. By comparing the properties of light from distant objects to the light we observe today, scientists can infer whether the laws of physics have shifted over time. In particular, studies of distant quasars, supermassive black holes surrounded by swirling disks of gas, have provided valuable clues. Quasars are some of the most distant and ancient objects in the universe, and their light has traveled billions of years to reach us. By analyzing the absorption lines in the light from these objects, scientists can measure the fine structure constant at different points in the universe's history. If the constant has changed over time, it would suggest that the laws of physics are not as fixed as we once thought. The CMB also contains a wealth of information about the early universe, and it can be used to probe the conditions that existed when the universe was young. By comparing the CMB's temperature fluctuations with theoretical models, scientists can determine whether the constants of nature have remained the same since the beginning of time. Some researchers have studied supernovae to explore the possibility of varying constants. Supernovae serve as natural beacons in the universe, helping astronomers measure distances and track the expansion of space. If the laws of physics were different in the past, supernovae might behave in unexpected ways, providing another clue that the constants have shifted over time. For example, the energy output of supernovae could be influenced by changes in the strength of gravity or the electromagnetic force. Some scientists argue that the constants of nature are likely to be fixed, and that any apparent changes in their values could be due to other factors, such as the limitations of our measurements or the assumptions built into our models. Others suggest that the changes may be so small that they are not detectable with current technology. However, the possibility remains that the universe is more dynamic than we realize, with the potential for the laws of physics to evolve as the universe itself changes. If it turns out that the laws of physics do evolve over time, it would suggest that the cosmos is not a static, unchanging system, but a dynamic and evolving entity. The fabric of reality could be subject to change as the universe expands, with new laws emerging over time. This could mean that the universe's future is not determined by the laws we currently understand, but by an entirely new set of rules that emerge as space stretches and evolves. If the constants are not fixed, the future of the universe could unfold in ways that we cannot predict. The expansion of space might lead to the emergence of new physical laws, just as the universe's early moments were governed by conditions vastly different from those we experience today. If the constants change, the very nature of time, space, and matter could be rewritten, leading to a universe that operates under different principles. As our understanding of the universe deepens, we may come to realize that the laws of physics are not as unyielding as they once seemed. The idea that the constants of nature could shift as the universe expands opens up new avenues for exploration, pushing the boundaries of science and challenging our most fundamental assumptions about the universe. Whether these changes are subtle or dramatic, the possibility that the laws of physics themselves could evolve offers a glimpse into a universe that is not only vast, but full of surprises. Could dark energy be tapped as a resource? When the human mind encounters something so vast and powerful as dark energy, the natural question is whether it might someday be harnessed. Could dark energy, instead of being an abstract concept locked in the equations of cosmology, become a real and usable resource? Could an advanced civilization tap into the very expansion of the universe itself? The thought is not as strange as it may first sound. Throughout history, humanity has always tried to harness the invisible. Wind, magnetism, nuclear forces. At one time, each seemed intangible and beyond reach, yet they later became the foundation of technologies that reshaped civilization. In this light, dark energy is simply the latest mystery, the greatest unseen force. If its nature were understood, there may be ways to bend it to our will, or at least ride the wave it creates. But the first step in asking this question is understanding what dark energy really is, or more accurately, what it might be. At the moment, it is not pinned down to a single explanation. Each version carries different implications for whether it can be tapped or manipulated. If dark energy is truly a cosmological constant, the picture is difficult. A constant embedded in the very structure of space does not lend itself to extraction in any usual sense. It would be like trying to draw energy from the mere existence of geometry. Yet even here, some thinkers wonder if technology beyond our imagination could create ways to distort or funnel that expansion pressure. After all, expansion is not an abstract metaphor. It is a measurable effect that changes the distances between galaxies. In principle, a device capable of amplifying or redirecting that effect could function as a kind of cosmic engine. If, however, dark energy is a dynamic field like quintessence, the possibilities widen. Fields are not unfamiliar in physics. Electromagnetic fields, for example, are tapped every day in devices that power our modern lives. If quintessence is real, it might carry fluctuations, gradients, or interactions that could be exploited. Perhaps an advanced civilization could learn to surf on regions of stronger expansion or harvest energy from the way the field changes over cosmic time. This would require a level of understanding and control that makes our current technology seem like fire-making compared to fusion reactors, but it does not necessarily break the laws of physics. Even more speculative are the ideas that link dark energy to the vacuum of space itself. The vacuum energy of this quantum froth may be related to what we call dark energy. If so, then perhaps the same way we manipulate quantum fields in laboratories to create lasers, superconductors, or particle collisions, a far future intelligence could manipulate vacuum energy on cosmic scales. In this view, dark energy becomes less like an unreachable background and more like an untapped reservoir hidden in plain sight. What could such a resource mean in practical terms? Imagine a civilization that has already harnessed all the energy from its planet, then from its star, then from its entire galaxy, a civilization climbing the rungs of the Kardashev scale. At some point, even galaxies run dry, stars die, black holes evaporate, and ordinary energy sources fade. But dark energy is not tied to stars or matter. It is tied to the structure of the universe, and as far as we know, it is eternal. A civilization that could tap it would have, in effect, an endless supply of power. Not just endless, but ever-growing. One can picture technologies built around this idea. Ships that do not burn fuel, but ride the expansion like surfers on a cosmic tide. Habitats powered not by fading starlight, but by the stretching of space-time. Engineering projects so immense that they do not just use dark energy, but guide its flow, shaping the destiny of their galaxies. To us, these images feel like science fiction, but the very fact that expansion exists suggests that it is, in principle, a phenomenon with structure, and where there is structure, there is potential for exploitation. There is also a survival angle. If the universe's future is shaped by dark energy, then understanding it is not just curiosity, it is necessity. A civilization might need to learn how to adapt to an accelerating universe to avoid being stranded in isolation. In trillions of years, galaxies beyond the local group will fade from view, carried away faster than light by expansion. If expansion is energy, then those who can tap it may be able to bridge the widening gulf, keeping contact with the cosmos when others are left behind in darkness. But there are dangers too. Harnessing dark energy may not be safe. After all, if it is linked to the vacuum of space or the balance of cosmic forces, tampering with it could destabilize reality. Theoretical physics has long whispered about vacuum decay, a scenario in which a disturbance could trigger a shift in the energy state of the universe, rewriting the laws of physics in an unstoppable wave. A civilization probing dark energy might risk awakening something catastrophic. In this sense, dark energy as a resource could be both the ultimate salvation and the ultimate danger, a double-edged blade sharper than anything we have ever used. For now, these ideas remain deep speculation. Humanity cannot even generate a precise definition of what dark energy is, let alone build machines to interact with it. We measure its effect only on the largest scales, through galaxies drifting apart. No laboratory experiment has touched it directly, but that has never stopped science before. The leap from watching lightning to building power plants was enormous. The leap from knowing the atom exists to splitting it was even greater. It may be that civilizations older than ours, perhaps billions of years ahead, have already walked this path and learned to drink from the cosmic reservoir that surrounds us. The universe is not just vast in space, but vast in opportunities we cannot yet see. Somewhere, perhaps, beings live not by starlight but by the stretching of space, thriving in a cosmos that for us is still a mystery. The fact that we can even ask the question, could dark energy be tapped, is itself a measure of human imagination. Whether it will ever shift from imagination to reality remains a great unknown. Could technology let us outrun cosmic expansion? Is the cosmic horizon a true limit, or is it a challenge that could be overcome with technology? The first idea that comes to mind is speed. What if we simply traveled fast enough to reach galaxies before they cross the horizon? The problem is that nothing can move faster than light through space. This means traditional propulsion, no matter how powerful, cannot outrun the horizon. It is a rule built into the very geometry of space-time. But rules in physics sometimes bend when looked at through new perspectives. One such perspective is wormholes. A wormhole, if it can exist, is like a tunnel through space-time. It does not take you faster than light through ordinary space. Instead, it shortens the path. Imagine folding a piece of paper so two far apart points touch. A wormhole is the crease where the paper meets. If a civilization could stabilize such a structure, perhaps it could step around the limits of expansion. Even if a galaxy is sliding away at faster-than-light recession, a shortcut could reconnect it. However, wormholes are not only theoretical but also unstable in all current models. They collapse before anything can pass through. To keep one open would require exotic matter, a form of energy with negative pressure. Strangely enough, dark energy already has negative pressure. It is what drives expansion. Some physicists wonder if the same property that separates galaxies might, in principle, allow bridges to form. Another idea comes from the concept of warp drives. In popular imagination, a warp drive bends space around a ship, creating a bubble that moves faster than light relative to the outside universe. The ship itself never breaks the speed of light locally. Instead, space-time contracts in front and expands behind, pushing the bubble forward. The most famous version of this idea is the Alcubierre drive, proposed in the 1990s. Mathematically, it works. The equations allow a bubble to move any distance, even outrunning expansion. But there is a catch. The energy required is absurd. Early calculations suggested you would need more energy than the entire universe contains just to move a single ship. Later refinements reduced that figure, but it remains far beyond anything realistic. Still, it raises a fascinating possibility. The same expansion that isolates us might be manipulated, controlled, even ridden like a wave. Manipulating space-time directly is another path of speculation. Today, we treat cosmic expansion as something that simply happens. We cannot turn it on or off. But what if a civilization advanced far beyond us could adjust the density of dark energy locally? If expansion is caused by vacuum energy, perhaps vacuum energy can be engineered. Imagine building machines that create regions where expansion reverses. In those pockets, galaxies would stop drifting away. Over immense timescales, one could imagine harvesting parts of the universe by freezing them in place while the rest continues to slip away. The horizon would no longer be a permanent border, but a condition that can be managed. Even without exotic engineering, some dream of navigating around expansion by exploiting natural spacetime structures. Black holes, for instance, bend spacetime so severely that they act like natural funnels. If connected to a wormhole, they might serve as gateways to distant regions. Cosmic strings, hypothetical one-dimensional defects from the early universe, could also distort spacetime in unusual ways, potentially acting as shortcuts. These ideas are not supported by observation yet, but they linger in the imagination because they fit the theme. The universe sets up a wall, and intelligence looks for a door. One way to think of outrunning expansion is not to chase galaxies, but to carry them with us. Some theoretical proposals suggest that advanced civilizations could move entire stars. By using gravitational assists, building megastructures, or manipulating stellar energy output, stars could be nudged gradually into stable groups. Over trillions of years, civilizations might herd their galactic neighbors into tight clusters that resist expansion. Instead of outrunning the horizon, they would reshape their local island of the universe to survive within it. This approach accepts the limit, but sidesteps its consequences. Where others see a cosmic prison, this view sees a garden to be tended. We are explorers. We want to see what lies beyond, to keep reaching outward. But from another perspective, it may not matter if galaxies slide away. Life, even advanced life, only needs a finite amount of matter and energy to sustain itself. If a civilization can master its local cluster of stars, perhaps that is enough. Maybe outrunning expansion is about the human need to reach what is forbidden, to push past the edge. Whether or not the horizon can be crossed, the urge to try seems almost inevitable. Every attempt to imagine technologies that outrun expansion shares a common theme. They all involve bending space-time itself. Rockets, no matter how powerful, remain trapped. To escape, one must stop treating expansion as a backdrop and start treating it as a material to be shaped. If it is ever possible, the horizon might be less of a wall and more of a puzzle waiting for the right solution. Cosmic engineering. creating islands in an expanding sea. Cosmic engineering, as it is sometimes called, is the thought that instead of being passive observers of the universe's fate, life might actively reshape entire regions of space. In practice, this could mean directing the motion of stars, entire solar systems, or even galaxies into closer orbits, so they remain bound to one another despite the cosmic stretching of space. The result would be an artificial cluster, a hand-built collection of stars that would endure even as the wider cosmos becomes empty. This would be like building a raft in an endless ocean. The raft cannot stop the sea from rising, but it gives its passengers a platform to survive upon. The scale of such an effort is hard to grasp. Moving a single star is already beyond anything we can imagine today. Stars are not small engines one can simply tug across space. They are enormous balls of plasma with the mass of millions of Earths. Yet, physics offers, at least in theory, ways this might be possible. For example, using gravity assists, civilizations could direct massive objects, like asteroids, black holes, or even entire stars, into carefully designed flybys that gradually shift stellar orbits. Over millions of years, tiny nudges could accumulate into significant movements. This would be slow, but in cosmic terms, slowness is not necessarily a weakness. After all, the timeline for galaxies to drift away is measured in tens of billions of years. With enough patience, there is time to build the raft. Another possibility is using directed energy, like enormous lasers or controlled fusion reactions, to propel stars. In principle, if you can reflect light off a star or use jets of material as thrusters, you could slowly alter its trajectory. Some concepts even imagine stellar engines, devices that harness part of a star's output and redirect it to generate thrust. Over unimaginable timeframes, stars could then be moved into formations, forming dense clusters of resources. This shifts the story of the universe from passive fate to active choice. If life becomes powerful enough to attempt such engineering, then the end of the universe may not be entirely beyond influence. It could stop dark energy from pulling the wider cosmos apart, but within certain boundaries, civilizations could create regions of stability. These engineered clusters might survive as tiny pockets of activity in an otherwise frozen, empty universe. They would not defeat cosmic expansion, but they would carve out sanctuaries against it. If the future of life is to be squeezed into ever-shrinking regions of usable matter, then gathering that matter ahead of time becomes not just a technical project, but a matter of survival strategy. A civilization that ignores the cosmic horizon might eventually find itself stranded on a single star system, cut off from everything else. One that acts early could preserve billions of stars in its engineered island. Some astronomers speculate, though very cautiously, that unusual galactic formations could one day be found that do not follow the expected natural patterns. If intelligent life really can rearrange stars or galaxies, then perhaps some regions of the universe might already bear their fingerprints. Of course, we have no idea whether civilizations ever last long enough to attempt something so immense. The timescales involved, billions or even trillions of years, are far beyond any human history, but thinking about them forces us to imagine what intelligence might mean when measured not in centuries but in cosmic epochs. If life continues, it must adapt not only to local challenges like climate or asteroid impacts, but also to the changing structure of the cosmos itself. Expansion is not something we notice day to day, but on the scale of eternity, it is the central fact of existence. To respond to it, life may one day need to think bigger than galaxies, bigger than physics, as we practice it now, and imagine engineering projects that seem impossible by any reasonable standard. Whether or not such projects are ever real, they represent one of the boldest visions of what survival might mean in a universe destined for isolation. The cosmic neutrino background, a shadow of the earliest motion. The cosmic neutrino background is one of the strangest and most hidden relics of the early universe. It is often compared to the CMB, but in truth, it goes back even further in time. While the CMB comes from when light was finally free to move across space, neutrinos were already streaming long before that moment. They are the messengers of an even earlier universe, carrying information from a period we cannot otherwise touch. Unlike light, which was trapped by the dense plasma for hundreds of thousands of years after the Big Bang, neutrinos were free after just 1 second. That means they could tell us about what the universe looked like, not after hundreds of thousands of years, but after a single heartbeat of cosmic history. Neutrinos are peculiar particles. They hardly interact with matter at all, slipping through stars, planets, and even our own bodies, as though nothing were there. In fact, trillions of them pass through every person on Earth every second, and we do not notice. This ghostly nature makes them difficult to detect, but also makes them perfect carriers of information across unimaginable stretches of space and time. They do not scatter, they do not get absorbed, and they do not easily lose their story. The cosmic neutrino background is, in a way, the earliest preserved shadow of the universe's first motion, a frozen trace of energy that has been gliding across the cosmos for over 13 billion years. Detecting it, however, is like trying to hear a whisper in the middle of a roaring storm. The cosmic neutrino background is extremely faint and cold. After more than 13 billion years of cosmic expansion, the neutrinos have lost almost all of their energy. Today, their temperature is just about 1.95 Kelvin, only slightly above absolute zero. They move sluggishly compared to their early energetic state. If photons of the CMB are already faint and stretched into long microwaves, neutrinos are even more elusive because they barely interact with anything at all. Current experiments struggle to measure even the neutrinos coming from the Sun or from supernovae, which are far stronger signals. Yet, the cosmic neutrino background is even fainter than these by many orders of magnitude. Why then do scientists think it exists? The idea comes not from direct observation, but from theory. If the Big Bang model is correct, neutrinos must have been there in abundance. During the first second, the universe was so hot and dense that particles were constantly colliding and transforming into one another. Neutrinos were born in those interactions. As the universe expanded and cooled, neutrinos no longer interacted, and instead flew freely, preserving the conditions of that early second. Models of the early universe almost require their existence, and their faint fingerprints appear indirectly in other measurements. For example, the CMB, while being about light, also contains subtle hints that neutrinos were already present and influencing the way the universe grew. The distribution of galaxies and the formation of large-scale structures also carry imprints that match with the idea of neutrinos streaming in the early days. But the dream of science is not just to assume they exist, but to catch them directly. Some experiments are being built for this purpose. One of the most ambitious is called Ptolemy, a project that aims to measure the faint background neutrinos by capturing them using a special isotope of tritium. The idea is that relic neutrinos from the Big Bang might occasionally bump into tritium atoms in such a way that scientists could detect the energy difference. It would be a near impossible task, but if successful, it would be like opening a window directly into the first second of the universe. The excitement around this possibility is not just about proving a theory correct. If we could study the cosmic neutrino background, we could explore physics in a regime completely beyond what light can tell us. We could see how particles behaved before photons escaped. We might even find surprises, new types of particles, strange interactions, or evidence of physics that we do not yet understand. Neutrinos, because they are so faintly connected to the rest of the universe, may also carry information about conditions we have no other way of accessing. Some theories suggest that studying them could even give us clues about the unification of forces or the behavior of the universe in the very first fraction of a second. The CMB has often been described as the baby picture of the universe. The cosmic neutrino background would be an even earlier memory, not a picture but a shadow of its earliest movement, when the universe had only just been born. If we could ever listen to it, we would be hearing the first whispers of creation, an echo from a time when the cosmos was still in its infancy. We live in a universe filled with them, yet they are almost invisible to us. They are present in every star, every nuclear reaction, every explosion of a supernova, and yet they pass through our detectors mostly unnoticed. If we do detect the cosmic neutrino background, it will not come from building bigger telescopes or looking deeper into the sky. It will come from a kind of listening that is closer to silence than sight. It is about finding the faintest tremble of motion in particles that are everywhere but refuse to reveal themselves. Sometimes science tells us something must exist even when it seems impossible to ever see it. For decades, the CMB was a theoretical prediction, and then it was discovered almost by accident. The same could be true for the cosmic neutrino background. It may be that in the future, with better technology and cleverer methods, we will one day stumble upon its presence, confirming what theory has been whispering for so long. Gravitational waves as cosmic motion trackers. Gravitational waves are perhaps one of the most profound discoveries in the history of physics, and they hold incredible potential for revealing the deepest secrets of the universe. Unlike light, which travels in the form of electromagnetic waves, gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects. They move outward like waves on a pond and carry information about the events that created them. For centuries, humans have looked to the stars with telescopes, hoping to unlock the mysteries of the cosmos. But gravitational waves offer an entirely new way to observe the universe, by listening to the very fabric of space as it vibrates. The concept of gravitational waves was first predicted by Albert Einstein in 1915 as part of general relativity. He suggested that when massive objects, like stars or black holes, moved or collided, they would send ripples through space-time. These waves would travel at the speed of light, stretching and compressing space itself as they passed through. However, because gravitational waves are so faint and the sources of their creation are often incredibly far away, it was thought for decades that these waves would be far too weak to detect. That changed in 2015 when scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the groundbreaking discovery of gravitational waves from a pair of colliding black holes. This discovery confirmed Einstein's prediction and opened a new chapter in astrophysics. The detection of gravitational waves was not just an incremental step in our understanding of the universe, it was a paradigm shift. For the first time, scientists could hear the ripples caused by some of the most violent and energetic events in the cosmos. What makes gravitational waves particularly exciting is their ability to reveal cosmic events that are completely hidden from traditional telescopes. Unlike light, which can be blocked by dust and gas, gravitational waves pass through matter unimpeded. This means that they can carry information from the most distant corners of the universe, revealing events that would otherwise be invisible. Supernovae, neutron star mergers, and the collision of black holes can all create gravitational waves, and each one carries a unique fingerprint that scientists can analyze to learn more about the event itself. One of the most profound implications of gravitational wave astronomy is that it provides a way to track the motion of massive cosmic structures. Unlike conventional methods that rely on observing light or electromagnetic radiation, gravitational waves allow us to directly measure the warping of space-time. This is crucial for understanding the large-scale structure of the universe. By studying gravitational waves, scientists can observe the interactions between massive objects in regions where light does not travel or is blocked by other structures. Gravitational waves can also help us detect the presence of dark matter and dark energy. The interactions of these unseen forces can create disturbances in space-time that may be detectable through gravitational waves. In the future, the detection of these waves could give us new insights into the nature of dark matter and dark energy, helping to solve some of the most pressing mysteries in modern cosmology. Another exciting possibility is that gravitational waves could allow us to peer into the very early moments of the universe. In the first moments after the Big Bang, ripples in space-time may have been created by quantum fluctuations. These primordial gravitational waves, if detectable, could offer a direct window into the birth of the universe itself. Just like the cosmic neutrino background, primordial gravitational waves could provide a glimpse of the universe when it was only a fraction of a second old. Detecting these waves would be an enormous breakthrough, providing us with direct evidence of the conditions that prevailed in the early universe. In addition to their potential for revealing hidden cosmic events, gravitational waves also offer a unique way to study the motion of objects in the universe. For example, when two black holes spiral toward each other and eventually merge, they emit gravitational waves that encode detailed information about the masses and spins of the black holes, as well as the way they interact. By studying these waves, scientists can learn more about the properties of black holes, including their size, shape, and behavior. This is a crucial step in understanding the nature of these enigmatic objects, which are often difficult to study using traditional telescopes. The study of gravitational waves also opens up new possibilities for observing some of the most extreme environments in the universe. Neutron stars, for example, are incredibly dense objects, the remnants of massive stars that have exploded in supernova. These stars are so dense that a single teaspoon of neutron star material would weigh about 1 billion tons. When neutron stars collide, they send out gravitational waves that encode information about their mass, composition, and behavior. These collisions can also produce other fascinating phenomena, such as gamma-ray bursts, which are some of the most powerful explosions in the universe. Gravitational waves allow us to study these objects in ways that would be impossible with light alone. As gravitational wave detectors become more advanced, we will be able to observe even more subtle signals from across the universe. This will provide us with a much clearer picture of the motion of the universe on both small and large scales. For example, the detection of gravitational waves from binary neutron star systems could provide valuable insights into the formation and behavior of these stars, as well as the role they play in the creation of heavy elements like gold and platinum. Similarly, the detection of gravitational waves from supernovae could give us a better understanding of how these massive explosions occur and how they influence the evolution of galaxies. The study of gravitational waves is opening up new frontiers of exploration, allowing us to observe cosmic events that are hidden from traditional views. Gravitational waves offer a direct way to probe the largest and most violent events in the universe, and they may even reveal the hidden forces that govern the cosmos. As we continue to develop more sensitive detectors and improve our understanding of gravitational wave sources, we will gain unprecedented insights into the motion of the universe and the forces that shape its evolution. Leave a comment on what other aspect of the universe you'd like to explore next. If you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.